Hi, I'm Vladimir Podolsky, and today we are going to discuss divisibility. So we are used to numbers. We use them constantly, every day, everywhere in our life. But what is the reason that we have our numbers? Why do we have them to satisfy our needs? How it happened that we have specifically numbers we are having? So let's review the history. It all starts with counting. So the most basic task is to count some objects, and so we have numbers 1, 2, 3, and so on. Okay, and already now we have simple basic operations. We have addition and multiplication. They are possible. So, and these are basic tasks. So if we have, for example, two flocks and we unite them, then we need addition to count the number of sheep in the resultant flock. So addition and multiplication are possible. And okay, but what about inverse operations? Are they possible? So can we reverse operations we are having? Can we reverse addition and multiplication? Okay, and an inverse to addition is subtraction. So suppose we have added 4 to 5, so the result is 9. So now to obtain 5 back, we have to subtract 4. So subtraction is an inverse operation to addition. And in the same way, division is an inverse operation to multiplication. So suppose we have multiplied 3 by 4 and the result is 12. So now to get back our original number, we have to divide the result by 4 and the result will be 3. So are these inverse operations possible for our numbers that we are currently having, 1, 2, 3 and so on, numbers we are having to count? And it turns out that already subtraction is not always possible. For example, we cannot subtract 3 from 2 and obtain some positive integer. If we have a group of 2 objects, we cannot take 3 objects out of them. Okay, so we have a problem. We would like to have subtraction, and it is not always possible. So what is the solution? And the solution is very familiar and well known to us. We have to introduce negative numbers and 0. Note that these ideas look simple, so to add negative numbers and 0, but actually these are deep ideas, and it took humanity a lot of time to invent them. And these are actually two separate deep ideas. So now we have numbers 1, 2, 3 and so on to count. Now we have added number 0, and we also have added negative numbers -1, -2 and so on. And now subtraction is always possible. So here are some examples. 2 minus 3 is -1, and here are other examples. So the rules are well known. And also our original operations we already had, addition and multiplication, can be extended to negative numbers as well. So here are some examples as well, but again, the rules are well known. Now we have addition, subtraction and multiplication, and we have integer numbers, positive and negative. And but what about division? And it turns out that division is not always possible. For example, we cannot divide 3 by 2 and obtain some integer number. This is not possible. Again, so what is the solution? And the standard standard for us, but again, it's a deep idea, and to introduce rational numbers. We should consider fractions, and then 3 over 2 makes perfect sense. But sometimes it is important to stay within integers. Sometimes it is important to have an integer answer. Some things are not divisible, and we cannot consider fractions for them. And so we have to stay within integer numbers and not within rational numbers. So we have to live with the situation that division is not always possible. And so we arrive at number theory. Number theory studies integers and operations on them. And of course, basics of number theory have natural applications. So this is a very natural branch of mathematics. We study integer numbers and standard operations on them. So we have natural real-life applications. But it turned out that deep results in number theory had no applications. So if you consider more advanced, more involved results in regarding integers and operations on them, then they had no applications. And this was stated explicitly and well understood by top number theorists, including Hardy and Dixon, and they actually praised number theory for this. They talked about number theory as a branch of pure mathematics, mathematics for itself, and so on. Okay, does it mean that the number theory is useless? Does it mean that we do not have to study it? Of course, we have to study basics of number theory to have simple applications, but probably the rest is not needed at all. And it turns out that it's not anymore. Things changed dramatically in computer era. And here is the quote by Donald Knuth, a famous computer scientist. It turns out that results in number theory are important for high-speed numerical calculations, and so they are crucial for computer science. But this is only a part of the story. And another big part of the story is that number theory is vital for modern cryptography. And through cryptography, number theory dramatically affects our life. It is used in emails, in organization of messengers, in online transactions, and in the internet as a whole, and so on. So it affects many sides of our life, and so it is very important. So we have integer numbers, positive and negative, and division is not always possible over integers. So we have to identify the cases when it is possible. And for this we have to understand first what we mean by division. What does it mean that A is divisible by B? And here is the naive answer we can come up with. So just consider a rational number A divided by B. If it is integer, then A is divisible by B. If it is not integer, then is not divisible by B. And this is the correct statement, but it is not very good as definition. And the reason is that this definition reduces our question to a notion that is more complex than the notions we are currently having, the notion of rational numbers. So, to come up with better definition, let's unwrap what we are currently trying to say. What we are saying that when we say that A divided by B is integer. Okay, so what does it mean that A over B is integer? It means that the denominator cancels out in this fraction. And it means that A can be represented as a product of two integers, one of which is B and another is some other integer k. And this means that A is B times k, and then we have that our fraction is B times k over B, and B cancels out, and the result is k, so A over B is an integer number. So A over B is integer if A is representable as a product of two integers, B and some other integer. And now this reformulation uses only simple notions, the notion of product, and that's it. And so this will be our formal definition. A is divisible by B, or B divides A, and we denote it like this, if there is an integer k, such that A is the product of B and k. And if A is not divisible by B, if B doesn't divide A, we denote this in this way. And this definition has a very simple intuitive sense. So here is the definition of divisibility again. And the intuition is the following. And for simplicity, assume that A and B are positive. So suppose we have A objects, and we would like to split them in groups of size B. And then it is possible if and only if A is divisible by B, and K will be the size of the number of groups. So we have K groups of B objects, the number of objects in all groups is K times B, and it should be equal to A. Let's consider several examples. For example, number 15 is divisible by 3. And indeed, we can pick k to be equal to 5, and 15 is equal to 3 times 5, so 15 is divisible by 3. We have introduced our notion of divisibility for negative numbers also. For example, 12 is divisible by minus 4. And here we can pick k to be equal to minus 3, so 12 is minus 4 times minus 3, and 12 is divisible by minus 4. And one more example, minus 24 is divisible by minus 6. And indeed here k can be equal to 4, and minus 24 is equal to minus 6 times 4. And final example, 15 is not divisible by 4. And indeed there is no such k such that 15 is equal to 4 times k. There is no such integer k. So 15 is not divisible by 4. Okay. But why do we care about formal definition if everything is very simple? So note that in our examples everything is simple, so we are dealing with simple notions now. Why do we care about some specific formal definition? And one of the reasons is that once we have a formal definition, we can show general properties. We can establish general properties of our notion. And here is an example. So suppose number c divides a and the same number c divides b as well. Then we can show that c divides sum of a and b and difference of a and b as well. And why this is true? Note that since c divides a and c divides b, then we know that a and b has the following form. A is c times k1 for some k1 and b is c times k2 for some k2. Okay, and then we can add or subtract a and b and then obtain that a plus b is equal to c times k1 plus k2 and a minus b is equal to c times k1 minus k2. And so a plus or a minus b has the same form, and by definition a plus b and a minus b are also divisible by c. So using our formal definition we can establish this general property, which is true for all numbers. Here is another example. Suppose b divides a. Is it true that b divides 3 times a? Yes, it turns out to be true. And again, we can just use definition of divisibility. B divides a means that a is equal to b times k for some integer k. And now we can consider 3 times a and note that using this previous equation, we see that 3 times a is equal to b times 3k. So 3 times a again satisfies the definition of divisibility by b. And so b divides 3 times a. And in the general case, we have the following. If b divides a and we have some integer c, then b divides a times c. And the definition, the proof here is basically the same. Again, we can just look at the definition of divisibility. B divides a means that there is some k such that a is equal to b times k. And so we can now look at the number we are interested in, c times a, and it is equal to b times c times k. And again, it satisfies the definition of divisibility by b. So b divides c times a as well. So division is not always possible. But we can generalize this notion to be applicable to all a and b. So suppose we have a positive integer b, and we will introduce division with a remainder now. The result of the division of a by b with a remainder is a pair of integers, q, which is called quotient, and r, which is called a remainder, such that a is equal to q times b plus r. And r is non-negative, but is at most b. And note that if r is equal to 0, then b divides a. Note that this notion, this definition, just turns out to be the definition of the fact that b divides a, if r is equal to 0. Okay. Now, what is the intuition behind this notion? So here is the definition again at the top of the screen. And the intuition is simple. So, and assume here again, for simplicity, that a is positive. So suppose we have a group of a objects and we would like to split it into subgroups of size b. And now we can pick these groups of size b one by one. And if we do it, then in the end we might have some number of objects left that are not enough to form one more group. And then this number of objects will be r, will be the remainder, and the number of groups we have formed will be q, the quotient. And so this formula will be exactly true. So we have q groups of size b, and we have additionally R objects left. And since R objects are not enough to form a new group, then R is less than B. So here is the intuition behind this definition. And let's consider some examples. For example, consider A equal to 15 and B equal to 4. Note that 15 doesn't divide 4. But still we can, it divides, so we can divide 15 by 4 with a remainder. 15 is equal to 3 times 4 plus 3. It can be easily checked. And then Q is equal to 3 and R is also equal to 3. Here is another example. We can apply division with a remainder to negative numbers. If A is 13 and B is 3, then we have the following equality. Minus 13 is equal to minus 5 times 3, which is minus 15, plus 2. And so Q here is equal to minus 5 and R is equal to 2. And one more example. Consider A to be equal to 12 and B equals 4, then 12 is 3 times 4 plus 0. And here the remainder R is 0, Q is equal to 3, and A is divisible by B. So let's get some more intuition. How do numbers that give the remainder 1 when we divide them by 7 look like? Let's look at them at the number line. So they all have the form A equals to Q times 7, we divide them by 7, plus 1, the remainder is 1. And Q here is arbitrary integer number. It can be 0, 1, 2, 3, and so on, and minus 1, minus 2, minus 3, and so on. Okay, so which numbers has this form? So one simple example is for Q equals 0, then A is equal to 1. Now here is 1. Now we have a sequence of numbers for positive Q. We have 7 plus 1, so for Q equals 1. We have 2 times 7 plus 1 for Q equals 2, which is 15. Then we have 22, and so on. Note that each next number is by 7 greater than the previous one. Finally, for negative Q, we have another sequence of numbers. For Q equals to minus 1, we have minus 7 plus 1, which is minus 6. For Q equals to minus 2, we have minus 2 times 7 plus 1, which is minus 13. And then we have minus 20, and so on. So note that here again, each next number is smaller than the previous one by 7. So we have this sequence of numbers, and note that between two adjacent numbers, the distance is 7. So each seventh number on the line has remainder 1. So, and that's how they look like. And in general, if we consider the numbers that give some fixed remainder R when we divide them by B, then in general we have the form A equals to Q times B plus R for all possible Q. And one example is for Q equals 0. This is just the remainder itself. A is equal to R. And then we have a sequence for positive Q, R plus B, R plus 2B, R plus 3B, and so on. So each next number is greater than the previous one by B. Then we have a sequence for negative Q, Q equals to minus 1, minus 2, minus 3, and so on. And the sequence is R minus B, R minus 2B, R minus 3B. Each next number is smaller by B than the previous one. And so, again, the distance between adjacent numbers that give the remainder R divided by, when we divide them by B, is B. And so each bth number has the remainder R. Let's discuss briefly why this is always possible, why we can always divide A by B with the remainder, why such Q and R exist. And the intuition is simple, we have already mentioned it. We can just do the following. We can take a group of A objects and we can form groups of size B one by one. And in the end, we will be left up with some amount of objects that is not enough to form a new group. And then the number of remaining objects is R, and the number of groups is Q, so intuition is simple. So we can restate it slightly more formally. So what we can do, we have a number A, and we can subtract B from it. We can subtract it once again from the result, and so on. So we can repeatedly subtract B from our number until we are left with a number which is less than B. And then the remainder will be r. The resulting number we are left with will be r, and the number of subtractions we have made will be q. And note that r is less than b because r is not enough to subtract b once again and to stay within non-negative numbers. What happens if a is negative? So here in this intuition, in this explanation, a is positive. What happens if a is negative? It's also simple. Just instead of subtracting b from a, just add b to a until you get a positive number. And then this positive number will be r, and the number of additions will be q. Now we have introduced the new notion, divisibility with the remainder. And there is a simple connection of this notion to the notion of divisibility. And here it is. If we have two integers a1 and a2, and they have the same remainder when we divide them by b, if and only if the difference is divisible by b. So here is the connection, and let's prove it. So suppose a1 and a2 have the same remainder, then a1 is equal to q1 times b plus r, a2 is equal to q2 times b plus r. So let's consider the difference. And note that the difference r and r cancel out, and the difference is q1 minus q2 times b. And just by definition, so we have the difference is b times some integer number, so just by definition b divides the difference of a1 and a2. Okay, so in the other direction, suppose b now divides the difference a1 minus a2. Then this means that there is some k, that a1 minus a2 is equal to k times b. And now a2 has some remainder when we divide it by b, so it has some form a2 is equal to q1 times b plus r for some r. And then we can substitute a2 into the first equality, and then we have that a1 is equal to a2 plus k times b. And then a1 is just equal to b times some number, q1 plus k, plus r. And this is exactly the form for division with remainder, and r here is a remainder. So the remainder of a2 when we divide a1 when we divide it by b is the same as the remainder of a2 when we divide it by b. Let's consider several problems in number theory. And consider the following problem. Suppose a is not divisible by 2, so a is odd. What possible remainders can a have when we divide it by 4? Okay, so there are 4 possible remainders for the number when we divide it by 4. The remainder can be 0, it can be 1, it can be 2, and it can be 3. So let's consider these cases and see which of them are possible. Okay, clearly the remainder 0 is impossible. If the remainder is 0, it means that a is divisible by 4. So it has the form 4 times some integer k. And so a is even. So, but we know that a is odd, so this case is impossible. Okay, there is one more similar case. Consider the remainder 2. So suppose a has remainder 2 when we divide it by 4, so a has the form 4 times some q plus 2. Note that here a is also even. Note that 4 times q is even and 2 is also even, so the sum of these numbers is also divisible by 2. So this is also impossible since we know that a is not divisible by 2. There are 2 remainders left, 1 and 3, and they are both possible. So clearly, so here are simple examples. A is equal to 1. And then, if we try to divide 1 by 4, then clearly the remainder is 1. And a is equal to 3 is another example. If we try to divide 3 by 4, the remainder, then the remainder will be 3. So, the remainders 1 and 3 are possible, and the remainders 0 and 2 are impossible. Let's consider the following problem. So, suppose we have 4 integers, a, b, c, and d. Can we say that 2 of them must have a difference that is divisible by 3? Can we say that for any 4 integers there are 2 among them such that their difference is divisible by 3? Okay, let's consider some examples. Let's just pick some numbers and see whether this is true or not. Let's pick number 1, 100, 27, and for example 5. Okay, let's look at these numbers. Can we find two of them that has difference that is divisible by 3? And indeed we can. If we subtract 1 from 100, then we have 99, which is divisible by 3. 99 is 3 times 33. We failed. We tried to find an example and we failed. So probably we should try to show that it is always the case. And indeed this is true. It turns out that this is always the case. Among any four numbers there are two such that their difference is divisible by 3. Why is it so? And the crucial idea here is the following. Just note that there are only 3 possible remainders when we try to divide numbers by 3. The remainders are 0, 1, and 2. And we have 4 numbers. So note that among these 4 numbers, at least 2 must have the same remainder when we try to divide them by 4. And so if we subtract these 2 numbers, as we already observed, the difference is divisible by 3. If 2 numbers have the same remainder when we try to divide them by 3, then their difference is divisible by 3. So it is always the case. Among any 4 numbers, there are 2 such that their difference is divisible by 3. Let's consider the next problem. Consider 3-digit non-negative numbers, and the question is the following. Suppose we are trying to divide them by 101. How many of the numbers will have the remainder 7 if we divide them by 101? And here in this problem we assume that 1-digit numbers and 2-digit numbers are also 3-digit numbers. We just start with zeros. So 3-digit numbers are numbers from 0 to 999. Okay, let's see how many numbers do we have in this problem. Let's look at all numbers that has remainder 7 when we try to divide them by 101. And all of them has the following form. A is equal to 7 plus q times 101. And q here is arbitrary integer number. Okay, let's look at all possible q, values of q, and see whether they fall in our interval, whether the result is between 0 and 999. Note that if q is negative, then a is clearly also negative, so these numbers doesn't fall in our interval. Now, the first number that falls in our range is for q equals 0. Then a is equal to 7 plus 0 times 101, which is just 7. So for q equal to 0, a satisfies our property. Okay, now we have q. The remaining q values of q are 1, 2, 3, and so on. And the number a grows when q grows. And the last q, such that a is still a 3-digit number, it is not hard to check that this q is equal to 9, then a is equal to 7 plus 9 times 101, which is just 7 plus 909, which is 916. The next a will be already greater than 1000. So this is the last q for which our number falls into this interval. So a falls in our interval, a is 3-digit, for q from 0 to 9. There are 10 such numbers q, so there are 10 such numbers, so there are 10 3-digit numbers that give a remainder 7 when we try to divide them by 101. So now we are in position to prove several divisibility tests. And let's start with the following problem. Consider the number 3756 and let's try to divide it by 10. What is the remainder and what is the quotient of this number? And note that the decimal system is convenient here. Indeed, we can consider our number and we can break it into 2 parts, 3750 and 6. And then the first number is divisible by 10. Now our number is equal to 375 times 10 plus 6. And note that this is exactly the expression of division of our number by 10 with the remainder. And so the remainder is 6 and the quotient is 375. So in general, we have the following. So note that this argument applies to any number. And in general, we have the following. Suppose we have some number and we divide it by 10 with a remainder, then the remainder will be just the last digit of our number, and the quotient is the number that is formed by digit of our initial number a, except the last digit. So we have the following simple observation, and note that it gives us a very convenient but also simple corollary. If you have some integer number a and it is divisible by 10, if its last digit is 0. Why it is so? Note that 10 divides a if and only if the remainder is 0, and note that the remainder is exactly, as we observed, the remainder is exactly the last digit. So 10 divides a if and only if the last digit is 0. Okay, now let's consider divisibility by 5. Okay, let's again start with the problem. Suppose we have a number 7347, and the question is it divisible by 5? And we can use the same trick here. Let's break our number into two parts. 7347 is equal to 734 times 10 plus 7. And now we can break it even more and note that okay, it is equal to 734 times 2 times 5 plus 5 plus 2. And note that the first two summands are divisible by 5. And the last one is not. And note that again it is the expression for division of our number by 5 with the remainder. And here the remainder is 2. And since the remainder is 2, then our number is not divisible by 5. Okay, and again we can generalize it. If you have any integer number a, it is divisible by 5, if and only if its last digit is 0 or 5. Okay, so let's give a proof. Let's just denote the last digit of a by b, and let's subtract b from a. And the resulting number has the last digit 0, and so it is divisible by 10, and so it is divisible by 5. So a minus b is divisible by 5, and so as we already shown before, this means that a and b has the same remainder when we divide them by 5. So the remainder of a is 0, if and only if the remainder of b is 0. So a is divisible by 5, if and only if b is divisible by 5. But b is divisible by 5 if b is a digit, so it's from 0 to 9, it is divisible by 5 if and only if it is 0 or 5. So we have shown our lemma. Some integer is divisible by 5 if and only if its last digit is 0 or 5. So it's very easy to check whether a given integer is divisible by 5. Okay, and let's also consider divisibility by 2. A very similar idea applies here. An integer is divisible by 2 if and only if its last digit is 0, 2, 4, 6, or 8. In other words, a is divisible by 2 if and only if its last digit is divisible by 2. And again, the proof is completely the same. So let's just denote the last digit of a by b. Let's subtract b from a. And now we have a number with the last digit 0. It is clearly divisible by 2. And so this means that a and b has the same remainder when we try to divide them by 2. And so a is divisible by 2 if and only if b is divisible by 2. And b is divisible by 2 if it is either 0 or 2 or 4 or 6 or 8. So let's review what we have learned in this lesson. We are studying number theory, and number theory deals with integer numbers and operations in them. Number theory is important for fast numerical computations, and also it is vital for modern cryptography. So this is an important area. And we have discussed some basic notions, divisibility and remainders, and we will use them later on to build more advanced theory. Hi, I'm Vladimir Podolsky, and today we are going to discuss division by 2. So we have integer numbers, and let's consider division of these numbers by 2. There are two possible remainders that numbers can have when we divide them by 2. The remainder can be 0 or it can be 1. And if the remainder of some number is 0, then this number is divisible by 2. And these numbers are called even numbers. And if the remainder is 1, then this number is not divisible by 2. And these numbers are called odd numbers. Okay, let's consider the following problem. Suppose we have two classes, and one with A students and one with B students. And we unite these classes, and we would like now to split all of the students into pairs to work on a project. Is it possible to do that, to split all students into pairs, if A is even and B is odd? And the same question we can ask if both of the numbers are even, and the same question we can ask when A and B are both odd. Okay, let's start with the first question. Suppose A is even and B is odd. What we can do now? Now we can split all students into pairs in the first class. Because A is even, so we can split all students into pairs. A is divisible by 2. And in the second class, we can split all students into pairs, all students except 1 into pairs. There are odd number of students in B, so the remainder will be 1. So we can split everyone into pairs, all students into pairs except 1. One student will be left. So overall, we have 1 student left, and the answer is no, this is not possible. Okay, now consider the next case. If both A and B are even, then we can just split students into pairs in both classes separately. Since there are an even number of students in the first class, we can split them into pairs there. And since there are even number of students in the second class, then again we can split them into pairs. So here the answer is yes, we can do it. We can just split students into pairs in each class separately. Okay, and now the last question. If both A and B are odd, then what we can do? We can split students into pairs in the first class, and 1 student will be left. A is odd. And we can split students in the second class, and 1 student will be left again. B is also odd. So we have splitted almost all students, but 2 students are left. 1 from the first class and 1 from the second class. So we can pair 2 remaining students, and everyone will have a pair. So we have split students into pairs in all classes. So this is also possible, and the answer is yes here again. Okay, now let's restate this in our mathematical terms. So suppose we have 2 numbers A and B, and we know the remainders of A and B when we divide them by 2. Can we deduce the remainder of A plus B when we divide it by 2? Okay, it turns out that we can, and the idea is the same as in the previous problem. Okay, let's consider cases. If both A and B are even, so the remainders are 0, both for A and B, then they have the form 2 times Q1 and 2 times Q2. And so the sum has the form 2 times Q1 plus Q2. And it is an even number. The remainder here is also 0. So if both A and B are 0, so the sum is also if both A and B has the remainder 0, then the sum also has the remainder 0. Okay, now if one of the numbers is even and the other is odd, then we have the even number has the form 2 times Q1, and the odd number has the form 2 times Q2 plus 1. Okay, so now the sum has the following form: 2 times Q1 plus Q2 plus 1. And this is an odd number. So the remainder here is 1. So if A and B are, one of A and B is even and the other is odd, then the sum is odd. And the final case is the following. Suppose both A and B are odd. And then both of them has the form 2 times Q1 plus 1 and 2 times Q2 plus 1. So the sum will be equal to 2 times Q1 plus Q2 plus 1. Clearly this number is divisible by 2, so it is even. So overall we have the following table for the remainders of A plus B when we divide it by 2. The rows of the table correspond to the remainders of A, and the columns of the table correspond to the remainders of B. And then in the cell of the table, we write the remainder of A plus B. So if we consider the second row and the second column, then we consider the case when the remainder of A is 1 and the remainder of B is also 1, and so the remainder of A plus B, as we established, is 0. A plus B is even if both A and B are odd. Now consider the following situation. Suppose we know the remainder of A when we divide it by 2. Can we deduce from it what is the remainder of minus A? Minus A is also an integer number, so it also has its remainder. Okay, can we say what is the remainder of minus A? And yes, we can. And it is exactly the same as the remainder of A. So why it is so? Note that if A is divisible by 2, then minus A is also divisible by 2. And vice versa. If minus A is divisible by 2, then A is divisible by 2. So if A has the remainder 0, then minus A has the remainder 0. If A has the remainder 1, it is not divisible by 2, then minus A is not divisible by 2 as well, and the remainder of minus 2 is also 1. So now we can deduce the same result we obtain for the sum of two numbers. We can do the same for the difference of two numbers. If we have we consider the difference of two numbers A and B, and we consider the remainder of this number when we divide by 2, then this remainder is the same as the remainder of A plus B. And the reason is that minus B and plus B has the same remainder, so instead of subtracting B, we can add minus B, which is the same as to add B. So the remainder is the same. So for subtraction, we have the same table as for addition. So again, rows correspond to the remainders of A, columns correspond to the remainders of B, and in the cells we write the remainders of A minus B. It is the same as for addition. And now we can consider product. Suppose we know the remainders of two numbers A and B when we divide them by 2. Can we tell something about the remainder of their product, A times B? And it turns out, again, we can do it. The remainder of A plus A times B is completely determined by the remainders of A and the remainders of B. And let's consider cases. And there are two different cases here. If at least one of the numbers is even, so it is divisible by 2, and then the product is also divisible by 2. Note that if one of the numbers we are multiplying is divisible by 2, then the product is also divisible by 2. So if the remainder of at least one of the numbers is 0, then the remainder of the product is also 0. And the second case is when both A and B are odd. So then they have the form 2 times q1 plus 1 and 2 times q2 plus 1. So they are not divisible by 2, so the remainder is 1. And then let's just write down the product. It is q1 times 2 plus 1 times q2 times 2 plus 1. And then we can open the brackets and see that almost all summands will have multiplier 2. And so overall we will have q1 times q2 plus q1 plus q2, and all of this is multiplied by 2 plus 1. And this is an odd number, so it's easy to see that the last expression is exactly the expression for division with the remainder. And the remainder here is 1. So the number is odd. And so we have the following table for the remainders of A times B when we divide it by 2. Again, rows here correspond to remainders of A, columns correspond to remainders of B, and in the cell we write the remainders of A times B. So here the remainder of A times B is 1 if and only if the remainders of both A and B are 1. In all other cases, the remainder of A times B is 0. So now we can apply these rules to some specific problem. So suppose we have the following expression. So some numbers, and we apply addition, multiplication to them, and subtraction. And you would like to know what is the remainder of the resulting number when we divide it by 2. Is this number divisible by 2 or not? Is it even or odd? So Of course, we can do the calculation and then apply divisibility test for 2. We have to look at the last digit. But actually, using our rules, we can do it in a more simple way. We can do it without any calculations. So everything is simple. And the idea is the following. Note that the remainders of the results of operations addition, subtraction, multiplication depend only on the remainders of numbers we apply our operation to. So we can just apply our operations directly to the remainders, and then we will obtain the remainder of this number when we divide it by 2. Okay, so we can just substitute all numbers by their remainders. So note that 374 and 48 are even, so the remainders are 0. And for 419, 267 and 625 are odd, so their remainders are 1. So we obtain this expression, and now we can just do the calculation according to our tables. 1 times 0 for the remainders is 0. Now we have 1 plus 0 in the brackets, so the remainder will be 1. If we add odd number and even number, the result is odd. Now we multiply 0 by the bracket, and the result is always 0. So we have 0 minus 1, and for the remainders it means that the result is 1. So finally we have that the remainder of the resultant expression is 1. And this is the answer to our problem. So we can find the answer to the problem now without calculations. So the resultant remainder is 1, and so the remainder of our initial number when we divide it by 2 is 1. And so we can compute the remainder here without complicated computations. We do not have to compute the number to tell what is the remainder of this number when we divide it by 2. Let us recall what is the decimal system. So we would like to represent numbers by sequences of digits. Consider, for example, the following sequence of digits: 3, 9, 2, and 6. It represents the number 3926 in our decimal system. So, but what is this number? Note that this number can be written using arithmetic operations. It can be written as an arithmetic expression. So it is equal to 3000 plus 900 plus 20 plus 6. And now we can even modify it even more. We can say that it is 3 times 10 to the power 3 plus 9 times 10 squared plus 2 times 10 plus 6 times 10 to the power 0. 10 to the power 0 is just 1. Okay, so this is the way to express our number in arithmetic expression. And note that this is a general trick. It can be applied to any number. And in the general case, digits will be multiplied by powers of 10. So we have a sequence of powers of 10, and we multiply digits by them, and we add the results, and this is our number. This is the computation of our number. Okay, so note that each non-negative integer has a unique representation in this way in our decimal system. Okay, so now we can also consider a binary system. And the idea is that we can do just exactly the same, but instead of powers of 10, we will use powers of 2. And then this is called the binary system, and then we only have 2 digits, 2 bits, 0 and 1. Instead of 10 digits in this decimal system. And here is an example of a binary representation: 1, 0, 1, 1, 0, 1. And let's see which number it corresponds to. The idea is that we just write down, we multiply digits by powers of 2, and we add this up. So we multiply the last digit by 2 to the 0, which is just 1. The digit which is second from the end is multiplied by 2 to the 1. Then the previous digit is multiplied by 2 to the power of 2. And then the previous digit by 2 to the 3, and so on. Some of the powers of 2 are multiplied by 0 here, so overall we have here 2 to the 5 plus 2 to the 3 plus 2 to the 2 and plus 2 to the 0, which is 32 plus 8 plus 4 plus 1, and we can compute it. This is just 45. So we have expressed number 45 in binary system, in binary representation. Why do we even care? So why do we talk about binary system? Binary system is important for one simple reason. Computers use this system. So computers store information in binary system. So binary system is important. Okay, we can make the following observation relating binary system with division by 2. Suppose we divide a by 2 with the remainder. Then the remainder is just the last bit of a binary representation of a. And the quotient is the number which is formed by all bits of the binary representation of a except the last bit. Recall that we had a very similar statement for decimal system and division by 10. The remainder, if you try to divide a by 10, then the remainder is the last digit in decimal system. And here we have a very similar statement, but for division by 2 and binary representation. And actually the proof is basically the same. So for simplicity, just consider some specific number. For example, consider number 1, 1, 1, 0, 1 in binary representation. Okay, so let's write down this number. This is 1 times 2 to the 4 plus 1 times 2 to the 3 plus 1 times 2 to the 2 and so on. So if we look at these summands, note that all summands except the last one are divisible by 2. So we can move 2 out of the brackets, and so we have 2 to the 3 plus 2 to the 2 plus 2 to the 1 times 2 plus 1. And so this is the expression for division of our number with the remainder with division by 2. And 1 now is the remainder, and the expression in the brackets is the quotient. And note that what happened with the quotient, just all powers of 2 reduced by 1, and we removed the last summand from our original sum. So the quotient expresses the number with the same binary representation as the original number, but we just removed the last bit. So we have this lemma, and so the remainder is 1, and the quotient is 1, 1, 1, 0. And of course this proof applies to any number. We just consider some specific number for simplicity. Okay, now let's make the following observation. We do not prove here the correctness of binary system and what we are talking about. So we can ask the following question: why this system works? Why every integer can be represented here? Why the representation is unique? So why actually this system gives us unique representation for any number? So we omit the proof of this statement. However, note that the proof is not hard. And for example, it is possible to prove it. It is not hard to prove it using our previous lemma with combination with induction. So note that our previous lemma reduces the question of binary representation of A, reduces the construction of binary representation of A to the construction of binary representation of smaller number, of a quotient of A when we divide it by 2. So, and note that this is also a way to construct the binary representation of a given number. We can apply the previous lemma and recursion. So it is not hard to prove that binary system works. It has a unique representation for any number, but we will just omit this proof. Okay, now let's consider one more question related to the binary system. Suppose we have some number A. How many bits are needed to represent this number? Okay, let's start with some simple cases. Consider number which is 2 to the n. And note that we need exactly n plus 1 bits. 2 to the 4, for example, is 1 followed by 4 zeros. This is exactly the expression for 2 to the 4 in binary representation. So numbers of the form 2 to the n has simple binary representation 1 followed by n zeros. And note on the other hand that 2 to the n is the smallest number that requires n plus 1 bits. For example, consider 2 to the 4 minus 1. then it is not hard to see that it is equal to 2 to the 3 plus 2 to the 2 plus 2 to the 1 plus 1. This number has a binary representation 1, 1, 1, 1. So just 4 ones. So 2 to the n is the smallest number that requires n plus 1. 2 to the n minus 1 already, for 2 to the n minus 1, it is already enough to have n bits in binary representation. So we can extend now this to arbitrary number a. The number of bits that is needed to represent a in binary representation is determined by the largest n, such that 2 to the n is at most a. So note that if we increase number a, then 2 to the n is the smallest number for which we require n plus 1 bits in the representation. So if a is between 2 to the n and maybe equal to 2 to the n, but is strictly less than 2 to the n plus 1, then it requires exactly n plus 1 bits in the representation. And note that this is connected to the notion of logarithm. Let's recall that what is logarithm. Consider some real number x. So here we're not dealing with integers. Here x can be arbitrary real number, but it should be positive. Then by logarithm of x, we denote the number y, which is also real, such that 2 to the power of y is equal to x. That's just the definition of logarithm. And note that logarithm, what is the meaning of logarithm? Logarithm is the inverse function to exponentiation. So if we apply exponentiation to some number, if we consider some number y and consider the number 2 to the power of y, then logarithm is the inverse function. Logarithm base 2 of 2 to the power of y is equal to y. Okay, in particular, logarithm base 2 of 2 to the n is equal to n. So now we can connect the notion of logarithm to binary representations of integer numbers. And here is the statement. The number of bits that is needed to represent some integer a is equal to the integer part of logarithm base 2 of a plus 1. And here by integer part of x we denote the largest integer, which is less or equal than our possibly non-integer number x. So we apply this operation to some real number x and obtain an integer number which is less or equal than our x. So why this lemma is true, it is not hard to see now. And just recall that the number of bits in binary representation of a is equal to n plus 1, where n is the largest number, such that 2 to the n is at most equal to a. Now let's apply logarithm to both sides of the last inequality, and then we will see that n here is the largest number, such that n is at most logarithm of a. So n is exactly integer part of a. So we obtain our lemma. To represent number a in binary representation, we need n plus 1 bits, where n is integer part of logarithm base 2 of a. Hi, I'm Vladimir Podolsky, and today we are going to discuss modular arithmetic. Let's start with the following toy problem. What is the remainder of 17 times 12 times 19 plus 5 minus 23 when we divide it by 3? Okay, so this is not a complicated problem. We can just compute this number and find the remainder when we divide it by 3. This is nothing is complicated here. But let's ask the following question. Do we actually need to do this computation? So the computation of this number will take us some time. Do we actually need to do this computation? And is there probably a better way to do it, or just simpler and better way? And it turns out that there is. And to do this, we need to study remainders a little bit more. So for this, we will introduce congruence relations. We say that two numbers, a and b, are congruent modulo m if they have the same remainder when we divide them by m. So, and in case, we write this in the following way. Okay, let's discuss this new definition. Note that we have discussed before that two numbers a and b have the same remainder when we divide them by m, if and only if their difference is divisible by m. So equivalently, we can say that a is congruent to b modulo m if a minus b is divisible by m. And note now that which numbers are congruent to a modulo b, modulo m. These are all numbers that has the form a plus k times m for some integer k. So note that these are exactly the numbers, such that if we subtract a from a plus k times m, then the result will be divisible by m. So all numbers that are congruent to a modulo m has the form a plus k times m. And in particular, if r is a remainder of a when divided by m, then a is congruent to r modulo m. So a is always congruent to its remainder modulo some number m. Okay, congruence relations are very nice since they have some simple and convenient properties. And let's just discuss these properties. So if a is congruent to b modulo m, then a plus c is congruent to b plus c modulo the same number m. And this is true for any constant, for any number c. In other ways, if we take two congruent numbers and we add the same number to both of them, then the results will also be congruent. Okay, why this is true? And indeed, congruence of a and b modulo m means that m divides a minus b. But note that if we consider a plus c and b plus c, then the difference of these two numbers is the same as the difference of a and b. So a plus c minus b plus c is the same as a minus b. So if m divides a minus b, then m divides a plus c minus b plus c. It's just the same number. So a plus c and b plus c then are also congruent modulo m. Okay, and this rule can be easily extended. Now, if we have two congruences, a is congruent to b modulo m and c is congruent to d modulo m, then a plus c is congruent to b plus d modulo m. In other words, congruence is preserved under addition. If we take two congruences and we add them, add the left parts of the congruences and the right part of the congruences, then the result will be also congruent, the results of these additions. Okay, how can we prove it? It turns out that the proof is very simple using the previous rule. We can just do it in two steps. We can consider a plus c and first substitute c by d, and on the second step we will substitute b by d. Why both of these equations of these congruences are true? Note, so here are they just rewritten in two separate lines. Note that both of them are applications of the previous property. So in the first one, we have that c is congruent to d modulo m, and we just add some number a to both parts. And so the congruence is preserved. And in the second part, a is congruent to b modulo m. This is given to us. So we add d to both parts, and so now we have that a plus d is also congruent to b plus d modulo m. So in overall we have that a plus c is congruent to b plus d modulo m, and this is exactly what we needed. So congruence is preserved under addition. Okay, and now we can even these two simple observations can be used to show some simple to solve some simple problems. So let's consider the following problem. Suppose we have sum of several numbers 14, 41, 20, 13, 29, and the question is the sum divisible by 4? And actually, what is the remainder of this sum when we divide it by 4? Okay, of course we can compute the sum of these numbers and see what is the remainder of this number when we divide it by 4, but we do not have to do the calculation. Instead, we can apply the results we just obtained. What we can do instead, we can find the remainder modulo 4 such that it is congruent to our sum. So we can just write our sum, and now using our rules, we can substitute each summand by a congruent number. And let's just substitute each number by the remainder of this number when we divide it by 4. So 14 is 12 plus 2. So 12 is divisible by 4, so 2 is congruent to 14 modulo 4. And 1 is congruent to 41 modulo 4 because the difference is 40 and 40 is divisible by 4. 0 is congruent to 20 modulo 4, 20 is just divisible by 4. 1 is congruent to 13 modulo 4, and 1 is congruent to 29 modulo 4. 28 is divisible by 4, so 29 minus 1 is divisible by 4, so 29 and 1 are congruent. So if we sum up the results, this is much simpler than just sum up the original numbers, then we obtain 5. And 5 is congruent to 1 modulo 4. So our original expression is congruent to 1 modulo 4, and so 1 is the remainder of our original expression modulo 4. So now, these are not all properties of congruences we can actually prove. We can do basically the same with multiplication. So suppose A is congruent to B modulo some number m. Then A times C is congruent to B times C modulo the same number m for any constant C, for any integer C. Okay? What does it mean? It means that if we multiply two congruent numbers by the same number, the results are still congruent. And why is this true? Indeed, congruence of A and B means that m divides A minus B. But then m clearly divides C times A minus B. If we multiply A minus B by some number, then m still divides the same number. So we have this rule, and it can be easily extended. If we have two congruences, so we have A is congruent to B modulo m and that C is congruent to D modulo m, then A times C is congruent to B times D modulo m. In other words, congruence is preserved under multiplication. If we have two congruences, A is congruent to B and C is congruent to D, both modulo m, then product of the left parts of these congruences is congruent to products of the right parts of these congruences. Okay, and the proof is just like for addition. We can first substitute C by D and then substitute A by B. Again, let's write down both of these congruences separately and note that here we just apply the previous property twice. In the first part, we have a congruence of C and D. We are given that C is congruent to D modulo B, and we multiply them both parts by some number A. And in the second congruence, we have from the beginning that A is congruent to B modulo M. This is given to us. And then we multiply this congruence by some number D. The congruence is preserved, so we have both of these congruences, and together they give us that A is congruent, A times C is congruent to B times D modulo M. Okay, and now we are ready to solve the problem from the beginning of this lesson. What is the remainder of this expression when we divide it by 3? And the idea is that we can safely substitute all numbers in this expression by other congruent numbers. And instead of numbers in this expression, we can substitute, for example, the remainders of these numbers and compute the expression. It is much simpler. So the remainders here are 0, 1, and 2. These are possible remainders modulo 3. And so we can substitute all numbers by the remainders. The remainder of 17 is 2. 15 is divisible by 2, so the remainder is 2. 12 is divisible by 3. 15 is divisible by 3, so the remainder of 17 when we divide it by 3 is 2. 12 is divisible by 3, so the remainder is 0. 19 has the remainder 1, because 18 is divisible by 3, so 19 is 18 plus 1. And 5 has the remainder 2. Oh, and in the end, 23 has the remainder 2, because 21 is divisible by 3. And so here it is already easy to compute the result and find the remainder of this expression. But let's not do it. Even this is too complicated. We can actually even simplify this even more and learn one more trick at the same time. So observe that we can substitute these numbers by any congruent numbers we want. Not necessarily by 0, 1, and 2. We can pick any number here in the original expression and substitute by any congruent number modulo 3. So let's just do the following. We will use instead of numbers 0, 1, and 2, we will use 0, 1, and minus 1. Observe that 2 is congruent to minus 1 modulo 3. And so then, in the previous attempt, we just substitute all numbers 2 by minus 1, and the expression is even more simple. This is not very useful when we do computation modulo 3, but the same trick will be much more useful when we do computations modulo some more large number. But here we have this expression minus 1 times, in the brackets we have 0 times 1 minus 1, and plus 1 in the end. So in the brackets we have minus 1. So we have the first product is minus 1 times minus 1, which is 1. So we have 1 plus 1, which is 2. So our original expression is congruent to 2 modulo 3. And this is the remainder of our original expression modulo 3. Okay, let's consider some applications of our modular arithmetic. Consider the following problem. What are the last 2 digits of the number 99 to the power 99? And now we have a real problem, because the number here is actually large. It would be very nice not to compute this number. And note that here we again can use the reminders, and they can actually help a lot. So observe the following. The number consisting of 2 last digits of our number is actually the remainder of our number after the division by 100. If you consider some number a, and we can split it in sum of 2 numbers, the sum consisting of which is constructed from 2 last digits of this number, and the rest will be divisible by 100. So the number formed by last 2 digits of our number is exactly the remainder modulo 100. So we are interested in the remainder after the division of our number by 100. Okay, now let's consider this number, our number modulo 100, and we can apply our rules for modular operations. Note, first of all, that 99 is congruent to minus 1 modulo 100. Okay, and this will be a crucial observation for us, because now note that if we consider 99 to the power of 99, then this is just 99 multiplied by itself 99 times. And if we consider congruences modulo 100, congruence is preserved under multiplication. So we can substitute 99 by a congruent number. And so we can, instead of multiplying 99 by itself 199 times, we can multiply minus 1 by itself 99 times. So 99 to the power 99 is congruent to minus 1 to the power 99 modulo 100. And it is easy to compute minus 1 to the power 99. This is just minus 1. So we multiply minus 1 by itself odd number of times. So the result will be minus 1, which is congruent to 99 modulo 100. So our original number is just congruent to 99 modulo 100, and this is actually the residue, the remainder of our number modulo 100. So we have found the remainder, which is 99, and the remainder here is equal to the number formed by last 2 digits of our number. So last 2 digits of our number are 9 and 9. So we have solved our problem. Okay, let's consider the next problem. Consider the number 3,475. Is it divisible by 3 or not? Okay, so how can we approach this problem? We can compute the remainder after the division by 3. And if the remainder is 0, then the number is divisible. So instead of answering the question about divisibility, we can just compute the remainder, and the question about divisibility will be also answered. Okay, but how can we compute the remainder of this number? So observe that we can express this number as an arithmetic expression. And for this, we can just split 3,475 into 4 numbers: 3,000 plus 400 plus 70 plus 5. And so here we have, this is just a decimal system. So we have, this is the same as to say that our number is equal to 3 times 10 to the power 3 plus 4 times 10 to the power 2 plus 7 times 10 plus 5. So now we can apply modular arithmetic here. So we are interested in the remainder of this arithmetic expression, modulo 3. So we can just substitute numbers in this expression by numbers congruent to them modulo 3. Okay, let's observe the following. 10 is congruent to 1 modulo 3. So 10 is equal to 9 plus 1. So it's congruent to 1 modulo 3. 1 is the remainder of 10 if you divide it by 3. So now let's consider the powers of k. These are the most complicated part in our expression. So consider 10 to the power k. Since congruence is preserved under multiplication, then we can just substitute 10 in this expression by the number congruent to it. So 10 to the k is congruent to the number 1 to the k, modulo 3. And 1 to the k is just 1. So 10 to the k is congruent to 1 modulo 3. And so, in particular, we have shown that 10 to the k for any k gives a remainder 1 when we divide it by 3. And now we can go back to our expression. We have this number. We have expressed it in the sum of digits multiplied by powers of 10. And now we can observe that powers of 10 are congruent to 1, so we can just substitute all numbers, all powers of 10 here by 1. And so our number is congruent to number 3 plus 4 plus 7 plus 5 modulo 3. Okay, and now this number is just 19, which is congruent to 1 modulo 3. So our original number was congruent to 1 modulo 3. And this is the remainder of our number if we divide it by 3. So the remainder is non-zero, so our number is not divisible by 3. Okay, let's observe the following intermediate step in our solution. It is an important step. So we expressed our number in decimal system by multiplying digits by powers of 10. And then we observed that powers of 10 are congruent to 1 modulo 3. So we observed that this is congruent to 3 plus 4 plus 7 plus 5 modulo 3. And note that 3, 4, 7 and 5 are just digits of our original number. So we have shown that our number is congruent to sum of its digits modulo 3. Now also observe that we have this congruence 10 to the k congruent to 1 modulo 3 for all possible k's. So actually this step is applicable to all numbers in decimal systems. So if you have a number in decimal system, then it is congruent to sum of its digits. And so we have the following divisibility test for number 3. An integer a is congruent modulo 3 to the sum of its digits. In particular, a is divisible by 3 if and only if the sum of its digits is divisible by 3. So recall that any number is congruent to its remainder modulo m. So what we can do if we are talking about congruences modulo m, if we are looking for remainders modulo m, we can just represent any number by its remainder. And also recall that we have shown that arithmetic operations, addition and multiplication, preserve congruence. So if you would like to apply arithmetic operations to some numbers, and we would like to do it modulo some m, then we can apply them with operations to numbers that are congruent to the original numbers. So, for example, instead of applying operations to original numbers, we can apply them directly to remainders of the original numbers. And the remainder of the result of the operation depends only on the remainders of the original numbers to which we apply our operations. So what we can do, we can create tables for arithmetic operations for remainders over some module. And let's do it, for example, for module for m equal to 7. And here is addition table. So rows are labeled by one of the summonds, columns are labeled by the other summand, and in the cell on the intersection of a row and the column, we write the remainder of the result of addition. For example, if we consider the sum of 4 and 1, then we look at the row labeled by 4, look at the column labeled by 1, and in the intersection we have 5. So 5 is the remainder of the result if we add 4 and 1, and this is easy to see. And let's consider one more example. For example, let's consider 6 plus 6. So then we have to look at bottom right corner of this table, and here we have 5, and indeed if we add 6 and 6, it is 12, and modulo 7, it is congruent to 5. So 5 is the remainder of the result of addition of two numbers having remainders 6 modulo 7. So the remainder of the sum will be equal to 5. Note that this table has nice and simple structure. We can consider the same table for multiplication. Modulo 7. Again, we have a table. Rows of the table correspond to remainders modulo 7. Columns correspond to remainders modulo 7 again. And in the cell, we write the remainder, which corresponds to the product of the number in the row and in the column. Again, let's consider a couple of examples. For example, if we consider the product of 4 and 3, then it is 12, and the remainder modulo 7 is 5. So this is what we have in our table. And for example, let's consider again, let's consider now product 6 of 6 and 6. 6 by 6 is 36. Note that 35 is divisible by 7, so the remainder is 1, and this is what we have in bottom right corner of the table. So that's what we have. Now, note that using these tables we can perform modular computation. If we have some arithmetic expression with some numbers, we can substitute all numbers in the arithmetic expression by their remainders and apply operations according to the table. So each time we would like to apply an operation, we look at the table, just like with usual addition and multiplication table in school. We can just apply these operations one by one and do the computation. And also, these tables are convenient to observe properties of operations. And let's just try to do this. Let's just consider whether modular subtraction is possible. So what is modular subtraction? So let's consider the following question. Suppose we have two numbers, a and b. Is there such a number x such that a plus x is congruent to b modulo 7? Note that x will play a role of b minus a in our modular arithmetic. So is this always possible? And for this we can just look at this table, and we can observe that each row of this table contains all possible remainders. Okay, why is this good? Note that in this expression a plus x congruent to b, a plays the role of the row of this table, x plays the role of the column, and b plays the role of the value in the cell of the table. And the question is the following. So the question we are asking is, suppose we have some row of the table, and suppose we have some target value b. Is there a column such that in the intersection of our row and this column we have our target value? And note that in each row we have all possible values, so whatever row we are given and whatever target value we have, in any case there is some cell with this target value, and so there is some x which is equal to which satisfies this congruence, such that a plus x is congruent to b modulo 7. So this x exists for all a and b, and okay, what we can do now, we can consider this x given a and b, we can consider this x such that a plus x is congruent to b modulo 7, and note that the same argument holds for all modules m. So if I substitute 7 by any number m, still x exists. And x plays the role of modular subtraction. So it plays the role of b minus a in modular arithmetic. Note that the existence of x is natural. We can just pick b minus a as an integer and consider the corresponding remainder modulo 7. And the equation will be satisfied since congruence is preserved under addition. Okay, now let's consider modular division. Suppose we have two numbers, a and b, and now a should be non-zero. Is there such an x that a times x is congruent modulo times to b modulo 7? Okay, note that x corresponds to b divided by a in modular arithmetic. And note that a should be non-zero because, okay, if we multiply 0 by anything, it will be 0. So, of course, if a is 0, this is not always possible. But if a is non-zero, we can ask this question: is it true that x exists? And here we can look at multiplication table, and again we can see that that x always exists if a is non-zero. Again, each non-zero row, each row which is not the first one, contains all possible remainders. And again, a here corresponds to a row, b corresponds to the target value in this row, and x is a column. If we pick any row which is not the first one, then we can see all possible values in this row. So whatever target value, whatever b we have, there is a column having this value on the intersection with our row. So modular division is always possible. So given a that is not equal to 0 and b, we can always consider x such that a times x is congruent to b modulo 7. And we have shown that such an x exists, and again x plays the role of modular division. It is b divided by a in modular arithmetic. Note that x is still some integer number, it's some remainder modulo 7. It just plays the role of division in our modular arithmetic. So everything is finally good, it seems like that, and the construction of modular arithmetic is complete. We have addition, multiplication, subtraction, division. Is this right? It turns out that no, and for this let's just consider some other module. Instead of 7, let's just consider 6, and let's consider multiplication modulo 6. And here is the table. And observe that rows that correspond to numbers 2, 3, and 4, they do not contain all possible remainders. So there are some remainders which are not presented here. And in particular, if we pick a to be equal to 3, so if we pick row labeled by 3, and we pick value 1 in the right hand side, then there is no such x, there is no such column such that 3 times x is congruent to 1 modulo 6. So this is not always possible. So for modulo 7 we found that modular division is always possible, and for modulo 6 it turned out to be not the case. So what is going on? Why it happens that we have division modulo 7, but we do not have division modulo 6? What is the difference between 7 and 6? Why it works in one case and doesn't work in the other? And it turns out that the modular division is actually more complicated than it seemed before, than we seemed after we considered modulo 7. And we will discuss these differences, these complications in further in this course. We will see what is the difference between 7 and 6 that makes division impossible for modulo 6. Okay, let us discuss what we have in this, what we had in this course. We have started with some simple notions, divisibility and remainders. And then from them we developed more advanced things. We developed the basics of modular arithmetic. We have addition, multiplication, subtraction, modulo some number. But things are complicated and we do not understand them completely. So the division turned out to be complicated. Okay, is it bad that things are complicated? Is it bad for us in any sense? And in some sense, yes. We would like things to be more simple because we would like to use our number theory for computations. We would like to compute things effectively. And if something is complicated, it is harder for us to compute. But maybe in some sense complicated is good. And it turns out that yes, this is true. Complicated things are also important, and they are crucial for cryptography. Cryptography relies on things that are hard to compute. So if we have something that is hard to compute, this is actually, in some other sense, this is good for us.
Hello everybody, welcome to the module devoted to the Euclid's algorithm. This is an efficient algorithm for computing the greatest common divisor of two integers a and b. So just by definition, the greatest common divisor of a and b, where a and b are any integers that are not both equal to 0, is the largest number that divides both a and b. So any number that divides both a and b is called a common divisor of a and b. So the greatest common divisor is the largest such number. For example, the greatest common divisor of 24 and 16 is equal to 8. So it is not difficult to check that 8 divides both these numbers and that any larger number does not divide at least one of them. For example, 16 divides 16, of course, but does not divide 24. Another example, the greatest common divisor of 9 and 17 is equal to 1. So in a sense, 9 and 17 do not share any non-trivial common divisors. Okay? So why do I say non-trivial? Well, this is just because 1 divides any integer number. So any two integer numbers have 1 as a common divisor. Okay? So the last example is that the greatest common divisor of 239 and 0 is equal to 239 itself. So this is just because no larger number can divide 239 on one hand, and on the other hand it definitely divides 0 just because any non-zero number divides 0. Okay? So the last remark about this definition is that in this definition we allow a and b to be any numbers, positive or negative, with the only requirement that they are not both equal to 0. On the other hand, throughout the lecture we will assume that both a and b are non-negative. We can do this without loss of generality just because if you have a number a which is positive and the number minus a which is negative, they have the same set of divisors. Okay? So if you have a negative number a, you can as well consider the number minus a which is positive, and to find a common divisor of this number with some other number. Okay? Okay. So let me, before we proceed to the algorithm for computing the greatest common divisor, let me provide you with the motivation. So first of all, it turns out that computing the greatest common divisor of two integers is an essential operation for computing inverses modulo n. Namely, assume that we are given two numbers a and n, and what we would like to do is to find an integer k such that a times k is congruent to 1 modulo n. Or put it otherwise, a times k minus 1 is divisible by n. In this case, k is called an inverse of a modulo n. Okay? So this is an essential operation of many modern cryptographic protocols that are used billions of times per day. For example, when you purchase something over the web. Okay, so and we would like this operation to be computed efficiently, and for this it is important to have an algorithm for computing the greatest common divisor of two numbers efficiently. We will learn this a little bit later. Okay, another application is the following. Assume that we are going to work with rational numbers and we would like to perform some basic operations with such numbers. For example, to compute the sum of two such fractions. What you see here on the slide is a toy example. So to compute the sum of these two numbers, we are going to do the following. So we first multiply the first fraction, I mean the bottom part and the top part, with 59, and we multiply the second fraction with 177. Then they have the common bottom part, and we can write the sum as follows. Then we compute the number on top and the number of at the bottom, and what we get is the following number. So two large numbers. But it turns out that they do have a large common divisor, and we can cancel it out. So what remains is actually 2/3. So using greatest common divisors, we can simplify fractions. And this is exactly what happens, for example, in the fraction library in Python. So if you run these two lines of code in Python, then what you get is exactly 2/3 as an output. So the Python actually always finds the greatest common divisor of the top number and the bottom number for any fraction, and then cancels it out. And it is done very quickly, and we will soon learn how to compute the greatest common divisor quickly. So, but before proceeding to the efficient algorithm, let's just check whether the most naive algorithm is efficient or not. And by saying the most naive algorithm, I mean the following. So we are looking for the greatest common divisor. Let's just go through all potential candidates and let's select the greatest common divisor. Okay? So this can be implemented as follows. So let's go together through this code line by line. So in the first line, we actually check that A is non-negative and B is non-negative and A plus B is greater than 0. This actually ensures that not both of them are equal to 0. Okay? Then if at least one of them is equal to 0, then we just return the other number. Okay? In this case, nothing needs to be done, so we just return the maximum of them. We are sure that this is exactly the greatest common divisor. Then what we do in the next for loop is the following. So we have two positive numbers at this point. So we know that the greatest common divisor cannot be larger than the minimum of them. So what we're going to do is the following. We go from minimum of A and B, we go down to 1 by 1, and for any number we check whether it divides both A and B. If it does, then we stop immediately and we return this number. This is exactly what is happening here. So we go, D ranges from the minimum of A and B, step by step, I mean 1 by 1, down to so this -1 is responsible to the fact that we are going, at each iteration we're increasing D by 1, and we go till we reach 0, till we reach 1 actually. And then for each such D we check whether it divides both A and B. And if it does, we return D immediately. So in a sense, this return statement will never be executed in this code. Okay, so if we run, for example, GCD of 24 and 16, it will return 8 immediately. So you can try it on your laptop. Let's now analyze the resulting algorithm. So first of all, what we can notice is that if the greatest common divisor of A and B is equal to 1, then our algorithm will be forced to check all the possibilities, all the numbers from the minimum of A and B till 1. Okay, it will try all possibilities till it reaches 1, and at this point it will realize that the greatest common divisor is equal to 1, and it will return it. Okay, so now to check whether it is efficient enough or not, let's recall that our modern laptops perform roughly 1 billion operations per second. I'm not going to specify what is an operation, what is a basic operation, and also this is a very rough estimate, but it is at the same time, it is a pretty accurate estimate. So the problem is that in this case, if you consider these two numbers, if you run this code on your laptop, it will definitely take more than 1 minute. And this is just because these numbers are much larger than 10 to the 9. So these are actually roughly 100 billions or something. Okay? And so it will take more than 1 minute even for such short numbers. And when an algorithm or when some operation on our computer takes more than 1 second, we become mad immediately, right? So when we purchase something on the web, we would like to press a button and we would like our operation to be processed immediately. So we don't want to wait even for more than 1 second, right? So this is not an efficient algorithm, unfortunately. So, and even if we have a supercomputer to process such an operation, it will not be able to run this algorithm in less than 1 second, not to say more, if A and B are, say, 100 digits long. So, to be more precise, if you run the algorithm for A and B that are 100 digits long, even on a supercomputer that performs not just 1 billion, but 1 quadrillion operations per second, like millions of billions operations per second, then it will take this computer more than 100 years to find the greatest common divisor of such two numbers, which are not that great, which are not that big actually. So they are just 100 digits long. So this is not just like gigabytes or terabytes of data. These are just 100 digits. And our algorithm will not be able to compute the greatest common divisor even on a supercomputer. So we definitely need a more efficient algorithm. And this is what we're going to consider in the next part. So we will present or we will discover the Euclid's algorithm, which works much faster than our naive algorithm. In this video, we are going to discover together the famous Euclid's algorithm, which is, once again, let me remind you, an efficient algorithm for computing the greatest common divisor of two integers. It is based on the following simple but crucial Euclid's lemma. An integer d divides both integers a and b if and only if d divides a minus b and b. Let's prove it. So assume that d divides a and b. This actually means that a can be represented as d times p and b can be represented as d times q, where p and q are integers. But this also means that a minus b is equal to d times p minus q, right? So a minus b is divided by d just because p minus q is an integer. A minus b can also be represented as d times some integer, which is in this case equal to p minus q, right? For the other direction, assume that d divides a minus b and b. This essentially means that a minus b can be represented as d times p and b can be represented as d times q. But in this case, so what we need to prove in this case is that a is also divisible by d. But a is equal to a minus b plus b, right? Which means that a is equal to d times p plus q. So a is also of the form d times some integer number, which means nothing else that a is divisible by d again. Okay, so this is a simple enough lemma, and still let me also show you some visual explanation of this lemma. So consider some two numbers, for example 10 and 6. So they are both divisible by 2. This actually means that each of them can be kind of represented as some number of blocks of length 2. So, and also the difference between 10 and 6 is what is shown here on the slide, is this remaining part of 10. Okay, so if you align these two numbers by their left hands, then what is left out of 10 is exactly the difference between 10 and 6. So now, if you show these blocks of length 2, then it is visually clear that since 10 is composed of some number of blocks of length 2 and 6 is composed out of some number of blocks of length 2, the difference is also composed of some number of blocks of length 2. Okay? So this already gives us the possibility to implement the following algorithm. Let's do the following. So first of all, as usual, we first check that A and B satisfy the properties of our convention. So both of them are non-negative and not both of them are equal to 0. Okay, then we repeat the following procedure. If A is greater than B, we subtract B from A. If B is greater than A, if A is at least B, we subtract B from A. On the other hand, if A is smaller than B, we subtract A from B. Okay, and we do it while both of them are greater than 0. So what will happen? What will happen in the end of this while loop is that one of these two numbers will become equal to 0. So at this point, we will just return the maximum of these two numbers. So recall that if we have two numbers and one of them is equal to 0 and the other one is greater than 0, then the greatest common divisor of these two numbers is equal to that non-zero number. Okay, so this is an algorithm and you can run it. And you will notice that for small numbers it is fast enough. And moreover, if you have two numbers, for example, with 10 digits, it can work quite efficiently even on such long numbers. Still, unfortunately, there are still some numbers, some pairs of numbers for which this algorithm is not efficient enough. For example, if you can consider a number like this and a small number like this, then the resulting algorithm is going to perform too many operations. And it is not so difficult to understand the reason of such a bad behavior. So what will happen with these two numbers is the following. So the algorithm inside while loop will start to subtract 7 from this huge number. So it will do it again and again and again and again. So it will need to subtract 7 billions of times before this number will become smaller than 7, right? But let's try to understand what will be the remaining number when we stop subtracting 7 from it. So a little thought actually reveals that what is left is exactly the remainder of this number when divided by 7. Okay, so this is just by the definition of the remainder. So this is what is left when we subtract sufficiently many copies of 7 from these numbers. Okay, and this suggests us to change or to adjust our algorithm as follows. So instead of just subtracting a smaller number from the larger one, let's just take the remainder. So instead of subtracting, we will compute the remainder of A when divided by B, in case if A is at least B. In the opposite case, when A is smaller than B, we will replace B by the remainder of B when divided by A. So in the end, sum of these two numbers will become equal to 0 and we will return the maximum of A and B again. So when this is essentially the Euclid's algorithm. So as you see, this is a pretty simple algorithm. And what is also fantastic about this algorithm is that it is already efficient. So it can already process numbers with 100 digits easily. Even on your laptop, it will return the result in blink of an eye. So to be more precise, if, for example, if your numbers are 100 digits long, then the number of iterations of the while loop will be no more than 700. So, and it is very easy for modern computers to perform so many number of operations because they perform roughly 1 billion basic operations per second. Okay? Each iteration of our while loop is a division, which is not a very simple operation, but still it can be performed quite quickly. Okay? Now, let's to analyze why this algorithm is so efficient, let's first do the following. Let's just add some debug printing to our algorithm. So the only difference with the previous algorithm is that we added these two lines to the code. So at the beginning of each while iteration, we print the two current numbers A and B, and in the end we also print the resulting two numbers, and here we also print the result. So if you run this code for these two numbers shown at the bottom of the slide, then what you will see on your screen is the following. So to compute the greatest common divisor of these two numbers, the algorithm will try to compute the greatest common divisor of these two numbers. So this is essentially the remainder of the first number when divided by the second number. Okay, and then it will keep repeating the same procedure. But what is important in this output is that you can notice that our numbers are getting shorter and shorter and shorter and shorter. And this is essentially what happens with any pair of numbers. So what we're going to prove is that at each iteration of the while loop, if you have two numbers a and b, and assume for simplicity that a is at least b, okay, then after this while iteration, a is going to be dropped by at least a factor of 2. Okay, so at each iteration, the larger number drops by at least a factor of 2. But to be even more formal and precise, let me state it as a lemma. If we have two numbers, a and b, such that they are both greater than 0 and a is greater than b, then if you take a remainder of a modulo b, then what you get is a number which is strictly less than a divided by 2. Okay, now let's prove this. So for this, consider two situations. In the first case, b is at most half of a. So this is our first case. Then what we know is that a modulo b is a remainder of a when divided by b. Just by the definition of the remainder must be smaller than b itself. So we know that a mod b is smaller than b, and just by our assumption, it is at most a divided by 2. Or pictorially, you can look at this situation as follows. So this is a, okay? This is half of a, and we know that b is smaller than a, is at most a half, and we know that the remainder is even smaller. Then what we know is that a mod b is somewhere here. It is definitely smaller than a half. Okay. Now in the remaining case, when b is greater than a divided by 2, then what we actually know is that when you will divide a by b, you will actually get 1 and some remainder. Why just 1? Well, just because if you multiply this inequality by 2, for example, then what you get is that 2b is greater than a. Okay, so 2 copies of b is already greater than a. Okay, b plus b is greater than a. This means that when you divide a by b, you get 1 plus some remainder. And what is this remainder in this case? Well, this is just a minus b. So the picture is the following. This is a. This is half of a, and we know that b is greater than half of a. This actually means that b lies somewhere here, and this in turn means that a mod b, which is equal to a minus b, is smaller than half of a. Okay, so in both situations, a mod b is smaller than a half. And this is extremely good. So this means that at each iteration, like if you consider the binary representation of our numbers, then at each iteration, at least one of these numbers, the number of bits in the binary representation decreases at least by 1. Okay, or put it otherwise, at least one of our numbers is dropped by at least a factor of 2. This, in particular, means that if you started with two numbers, a and b, probably one of them was much larger than the other one, but in any case, the number of iterations of the while loop is at most binary logarithm of a plus binary logarithm of b. This is just because at some iterations you divide a by at least a factor of 2, by at least 2. At some iterations you divide b by 2. So this depends on whether a is greater than b or b is greater than a. But in any case, you cannot divide a by 2 for more than binary logarithm of a iterations. Okay, I mean, because after so many iterations, a is going to be equal to 0, and we will stop our while loop. And the same applies to b. So the total number of iterations is at most binary logarithm of a plus binary logarithm of b, which is great, because even if, for example, a consists of 5,000 decimal digits, This means actually that a is at most 10 to the power of 5,000. Then the binary logarithm of a is at most something like 17,000, which is nothing for modern laptops. So even if a consists of thousands of digits, it is perfectly fine for modern computers to find the greatest common divisor of such two numbers with the Euclid's algorithm. Okay, so it is very efficient. So as a final remark, let me also show you how to make this beautiful algorithm, how to make the code of this beautiful algorithm even more compact. So essentially it can be written just as one line of code. So if this is our common check that A and B are satisfy our properties, and actually here there is a small change. Here we assume that the first number is at least the second number. So actually we would like this algorithm to be called with two numbers such that the first one is at least the second one. Then we check that b is greater than 0, and then we check that they are not both equal to 0. Then what we do is the following. So if a and b are not equal to 0, then, and we know at this point that a is at least b, then we replace a with a remainder when divided by b. So what we get is some number which is smaller than b. And for this reason we actually swap here the parameters. We make a recursive call for b and a divided by b. So at this point b is greater than a divided by than the remainder of a divided by b. So this is the reason why b here is the first parameter of a recursive call. And we do this if a and b are non-negative. On the other hand, if b is equal to 0, then we just return a immediately. Okay? So this gives the following nice and compact implementation of the Euclid's algorithm. In this video, we are going to further extend the Euclid's algorithm for computing the greatest common divisor. Let's start with the following motivational question. So imagine that somebody computed the greatest common divisor of two integers a and b, and now would like to convince us that it is equal to d. So how can this be done? First of all, we can of course check that d divides a and b. This will convince us that d is indeed a common divisor of a and b, but this gives us no information whether it is the greatest or not, right? Because it is still not excluded that there exists a larger number than d that divides both a and b. It turns out, however, that to convince us that d is the greatest divisor of a and b, it is enough to represent it in the form ax plus by, where x and y are integers. Okay, let's prove it. Assume that d divides a and b, and assume that d is equal to ax plus by, where x and y are integers. Then necessarily d is equal to the greatest common divisor of a and b. So in a sense, x and y in this case is a certificate of the fact that d is the greatest common divisor of a and b. So let's prove this theorem. So first of all, since d divides a and b, it is a common divisor of a and b, and since GCD of AB is the greatest such common divisor, it implies that d is at most GCD of a and b. Once again, this is just because d is some common divisor of a and b, and GCD of a and b is the greatest common divisor. So some divisor is definitely at most the greatest common divisor. Okay? On the other hand, so GCD of a and b is some common divisor of a and b. But this means, in fact, that it should divide d. So why is that? So GCD of AB divides a and b. It means that it also divides a times x and b times y, and it also divides the sum of them. So we conclude that GCD of AB divides d. But this in turn means that GCD of a and b is at most d, because no number larger than d can divide d. So all in all, we conclude that d is equal to GCD of AB. Once again, this is just because we've just proved that D is at most the greatest common divisor of A and B, and at the same time, the greatest common divisor of A and B is at most D. So these two numbers are equal. Okay, so this is nice, and let me illustrate this with a couple of examples. So the greatest common divisors of 10 and 6 is equal to 2. And as you can see here, it indeed can be represented as a linear combination of 10 and 6. Namely, if you multiply 10 by -1 and if you multiply 6 by 2, and then you compute the sum, you get exactly 2. So this is -10 plus 12. It gives us 2. So the greatest common divisor of 7 and 5 is equal to 1, and it can be represented as 7 times -5 times -2, which gives us -14, plus 5 times 3, which is 15, so -14 plus 15 is equal to 1, which is the greatest common divisor of 7 and 5. So two more examples which are not so easy to compute by hand here on the fly, but still. So the greatest common divisor of 239 and 299 is equal to 23, and it can be checked that it can be also represented as a linear combinations of the numbers 391 and 299. Okay? Okay, now let's try to extend the Euclid's algorithm so that besides of computing the greatest common divisor itself, it also gives us a certificate and by a certificate I mean these two numbers x and y. So first of all, recall that the Euclid's algorithm that we discovered in the previous video does the following. To compute the greatest common divisor of A and B, it actually makes a recursive call for computing the greatest common divisor of B and the remainder of A divided by B. So this happens when A is at least B. Okay, so assume that we've just made such a recursive call, and it actually returned us not only the greatest common divisor D itself, but also a representation of this greatest common divisor of the linear combination of the parameters. And by parameters here, I mean these two parameters, B and A mod B. So the remainder of A divided by B. I assume that we know its representation, the representation of D as a linear combination of these two parameters. Namely that D is equal to BP plus A mod B times Q. So P and Q is a certificate in this case. So now what we would like to do is to transform this certificate into a certificate of the pair A and B. Okay, so for this we need a little bit of calculations. Okay, so we know that D is equal to B times P plus A mod B times Q. First of all, let's do the following. Let's rewrite A mod B using just A and B. So just by definition, A mod B is the remainder of A when divided by B. So this means that when we subtract enough copies of B, so what is left is some number which is smaller than B. Okay, so for this we need to subtract from A some number of copies of B. Okay, and this is exactly, so A divided by B, the integer part of A divided by B, is exactly what we get when we divide A by B. Okay, so this is the number of copies that we subtract. So A mod B is equal to A minus A divided by B. So in the integer part of it divided and multiplied by B. Okay, so when we rewrite it like this, we can now regroup all the terms. So what we see is that from here we get A times Q, and this is exactly what we see here. To get the multiplier for B, what we get is that this is B times P plus B, this B times A divided by B by Q. And this gives us the following expression. So this is a new certificate for A and B. So to get D, we need to multiply A by Q, and we need to multiply B by this expression. Okay, and this can be implemented as an algorithm, which is known as an extended Euclid's algorithm. So let's go through this code line by line once again. So again, we assume in this case that A is at least B, that the first parameter is always at least the second one. It is convenient in this case. So b is at least 0 and not both of them are equal to 0. So first of all, if b is equal to 0, so if smaller number is equal to 0, then we return the result immediately. So in this case, d, the greatest common divisor, is equal to a, to the larger number, right? And the certificate x and y are equal to just 1 and 0. Right, so x and y are equal to 1 and 0. So why is that? So recall that in this case b is equal to 0. So and d is equal to a. So a is represented as a times 1 plus b times 0. Which is clearly correct. So d is equal to a, so this is our greatest common divisor, and we represent it as a linear combination of a and b. So this is x, this is y. So in this case, the output is clearly correct. In the opposite case, when b is greater than 0, we make a recursive call. Recall that in this case we swap the parameters. So our first parameter is b, our second parameter is the remainder of a divided by b. This is just because we want our first parameter to be larger than the second one. So we make this recursive call, and it gives us the greatest common divisor and also a certificate pq. And using the formula from the previous slide, we compute the new certificate. So x is just equal to q, and y is equal to p minus q times a divided by b. And here we use this integer division. So this a divided by b gives us just exactly what we get, exactly an integer number, a divided by b. Okay, so this is why. So before returning the result, we check that d divides a, d divides b, and that d represents, d can be represented as a x plus by. So in the end, we return the result dxy. So as you see, just a simple extension of the original Euclid's algorithm allows us to produce not only the greatest common divisor, but also the certificate of this greatest common divisor. And we will use this essentially in the next part to compute inverses modulo n, which we discussed already as an essential part of modern cryptographic protocols. We now consider applications of the Euclid's algorithm, for computing the greatest common divisor. Our first application is computing the least common multiple of two integers efficiently. By definition, the least common multiple of two integers a and b, which are not both equal to 0, is the smallest integer which is divisible by both a and b. For example, the least common multiple of 24 and 16 is equal to 48. The least common multiple of 9 and 17 is equal to 153, which is just the product of 9 and 17, which is of course divisible by both 9 and 17. On the other hand, the least common multiple of 239 and 0 is undefined because we cannot divide by 0. Okay? Again, as with the greatest common divisor, we will assume that both a and b are non-negative integers, because if some number is divisible by a, then it is also divisible by minus a, of course. Okay, so one of the common applications of the least common multiple is working with fractions once again. So consider the following toy example. Assume that we would like to compute the sum of the following two fractions. So 31 divided by 177 and 29 divided by 118. So first of all, we would like to turn these two fractions to have the common denominator. And for this, it is enough to find the least common multiple, because we would like to find some small number. Of course, one possibility is just to multiply two denominators, but we can do much better. Namely, we can find the least common multiple of 117 and 177, and 118. In this case, it is equal to 354, and it is actually equal to 2 times 177 or 3 times 118. This allows us to rewrite these two fractions as follows. It is equal to 31 times 2, divided by 177 times 2 plus 29 times 3 divided, by 118 times 3. And this allows us finally to compute this sum, which finally gives us a result. And once again, using the least common multiple instead of just the product of denominators allows us to keep the numbers involved in these computations small enough. Okay? So, first of all, for computing the least common multiple, we can again just iterate through all possible potential candidates, starting from 1 to a times b. So we just go through all numbers from 1 to a times b and check whether the current number is divisible by a and b simultaneously. If it is divisible, we return immediately this number, right? So this gives us the following code. In this for loop, once again, we just go, we start with 1 and we go from 1 to a times b, and if d is divisible by a and d is divisible by b, we return d immediately. So in the worst case, we will return a times b, but if we are lucky, then we will find some smaller number. So as this is a small example, if we run it on the numbers 24 and 16, it will give us 48 as expected. So in the worst case, we will perform a times b checks. And this is bad enough for numbers like this. For example, if we have a number with 6 decimal digits and another number with 6 decimal digits, and if you run this algorithm, then it will take on your laptop definitely more than 1 minute, and this is something that we actually hate. So the question is, how can we apply the Euclid's algorithm for computing the greatest common divisor, for computing the least common multiple? You have probably guessed, of course, that we can do this, and in fact the formula is simple enough. So it turns out that for any two numbers a and b, the product of the least common multiple of a and b and the greatest common divisor of a and b is equal to the product of a and b. So this immediately gives us an efficient algorithm for computing the least common multiple. Namely, for computing the least common multiple, we just compute the greatest common divisor of a and b, and then we divide a times b by the greatest common divisor. This gives us the least common multiple. So the only remaining thing is to prove this formula. So let's do this. Assume that we are given two non-negative integers a and b. Then what we would like to prove is that the least common multiple of a and b is equal to a times b divided by the greatest common divisor of a and b. Okay? So let's prove it. Denote by d as usual the greatest common divisor of a and b, and assume that that a is equal to d times p and b is equal to d times q, where p and q are integers. Okay, so we know that p and q are integers just because d divides a and b. Okay, then first of all we notice that m equal to a times b divided by d is indeed a multiple of a and b. So why is that? Well, just because a times b is equal to dp times dq. So if we divide it by d, so on one hand it is equal to, we can cancel this p, this will give us p times dq, and this is equal to p times b, right? Because dq is equal to pb. I'm sorry, dq is equal to b. On the other hand, instead of cancelling this d, we can cancel this d. This will give us dp times q, and this is equal to a times q, right? Because dp is equal to a. Okay, so we know that this the m defined as follows is indeed a multiple of a and b. So what we now need to prove is that this is the smallest such multiple. So to prove that this is indeed the smallest one, let's assume the contrary. Assume that there is some other smaller multiple of a and b, denote this by m bar. Then we can define d bar as follows. It is ab divided by m bar. So we know that this is an integer just because m bar is a multiple of a and b. And we also know that this is greater than d, right? Just because m bar is smaller than b. And we know that d actually is equal to AB divided by m. Since m bar is smaller than m, we are dividing by a smaller number. This means that d bar is greater than d. And also it is not difficult to check that d bar divides a and b, just because a divided by d bar is equal to m bar divided by b, and b divided by d bar is equal to m bar divided by a. And both these numbers are integers just because m bar is, just by our assumption, is a multiple of a and b. So this contradicts to the fact that d is the largest common divisor of a and b, and this finally proves our lemma. Our second example, our second application of the Euclid's algorithm is solving Diophantine equations. These are polynomial equations in integer variables named after the ancient Greek mathematician Diophantus. Okay, so to introduce these equations, imagine the following situation. Imagine that you are at Cuba and you would like to purchase an apple. The price of an apple is 22 pesos. So the problem is that you only have 3 peso bills. Okay, and the cashier in turn only has 5 peso bills. So what you would like to do is to give the cashier some number of 3 peso bills, and in return you would like the cashier to give you some number of 5 peso bills plus an apple whose price is 22 pesos. So in a sense what you would like to do is to solve the following Diophantine equation. 3 times x is equal to 22 plus 5 times y, where x is the number of bills that you are going to give to the cashier and y is the number of 5 peso bills that the cashier is going to give you. So in particular for this equation there is a solution where x is equal to 9 and y is equal to 1. So let's check that it holds. So this is 3 times 9, so this is 27. This is 5 times 1, this is just 5, and the price of apple is 22. So indeed 27 is equal to 5 plus 22, right? And it turns out that there is another solution. So for example, you can use x equal to 14 and y equal to 4. Let's check once again. On the left hand side we have 42. Right here we have 5 times 4, which is 20, plus the price of an apple, which is 22. So again, this is a solution. Okay, so now imagine a different story. So you have a receipt with 2 blots in it. So what you can see from this receipt is that this is for some number of lamps. The price of each lamp is $49.36. I'm sorry. So what you also see is that the total price is some number ending with 7.29, and you would like to recover all the missing information. So the point is that in this case again you are going to solve some Diophantine equation. Let's try to come up with this equation. So first of all, you know that there is some number of lamps, denote this by x, and you know that the price of each lamp is 4936 cents. Okay, then you also let's denote by y the number which is missing here. So just by looking at this part of the receipt, you conclude that y consists of 3 digits. So y is some integer from 100 to 999. So y is at least 100 and y is smaller than 1000. Okay, and you know that in this case the total in cents is represented as follows. It is 1000 times y plus 728, right? So what you are going to solve in this case is the following Diophantine equation. So 4936x is equal to 100 times y plus 728. Where again x and y are integers, and you also have an additional restriction that y has 3 decimal digits. And it turns out that in this case the solution for this equation can be uniquely recovered. So you can easily recover all the missing information here, okay, which gives you the following solution. Okay, now let's consider two more examples. So, for example, consider the following Diophantine equation. 187x plus 55y is equal to 1, 2, 1. So one solution in this case is given by x equal to 3 and y equal to minus 8. Okay, so you can easily check that it is indeed a solution. And it turns out again that there is another solution where x is equal to minus 2 and y is equal to 9. And in fact, there are infinitely many solutions to this particular Diophantine equation. Okay? Now let's consider one more Diophantine equation, namely 187x plus 55y is equal to 45. It turns out that for this particular equation there are no solutions at all. And at this point it is very natural to ask why is that. So when a Diophantine equation has a solution. Okay, and this is exactly the subject of our next video. In this video, we are going to show how to solve Diophantine equations using the Euclid's algorithm for computing the greatest common divisor. The essence of our approach is the following theorem. Given three integers a, b, and c, where not both of a and b are equal to 0, consider the following Diophantine equation: ax plus by is equal to c. The theorem states that this equation has a solution if and only if the greatest common divisor of a and b divides c. Okay, so this is the necessary and sufficient condition for these Diophantine equations to have integer solutions. Okay, let's prove it. So denote by d the greatest common divisor of a and b, and assume that our equation has an integer solution. So since d divides a and b, and it is actually the greatest common divisor of a and b, we can represent a as dp and b as dq, where p and q are integers. Then consider some solution xy. Then c is equal to ax plus by, and this is equal to d times px plus qy, just because a is equal to dp and b is equal to dq. So as we see, d indeed divides c in this case. Okay. Now let's prove the remaining part. Assume now that d divides c. So our goal is to show that then our Diophantine equation has a solution. So since d is the greatest common divisor of a and b, it can be represented using extended Euclid's algorithm as ax plus by. Okay, then we know that c, let's represent it as a x bar plus b y bar. Okay, so x bar and y bar is the certificate, in a sense, of the fact that d is the greatest common divisor of a and b. Now we use the fact that c is divisible by d. Let's represent then c as td, and let's consider the following x and y. X is equal to t times x bar and y is equal to t times y bar. So what we're going to show is that this particular x and y is a solution to our Diophantine equation. So indeed, ax plus by is equal to t times a x bar plus b y bar. Okay, but this is equal to just t times d, which is equal to c. Okay, so in this case, indeed, xy is a solution. So once again, we've just stated and proved actually the necessary and sufficient condition for a Diophantine equation to have a solution. And in this case, what is needed is that d, the greatest common divisor of a and b, divides c. Okay, so let's give an example. Consider the following Diophantine equation: 10 times x plus 6 times y is equal to 14. Okay, so the extended Euclid's algorithm gives us the following representation for the greatest common divisor of 10 and 6. So 2 is equal to 10 times minus 1 plus 6 times 2. times 2, right? So this allows us to just multiply this equation by 7. So 2 multiplied by 7 is equal to 14, and we can also multiply by 7 the right hand side. This gives us 10 times minus 1 times 7 plus 6 times 2 times 7. So in a sense, what we have here, this is our x and this is our y, right? So x is equal to minus 7 in this case, y is equal to 14. Okay, so this gives us one solution. Okay, now let's consider another example. In this case, 391x plus 299y is equal to minus 69. Okay, so once again, in this case, the greatest common divisor of these two coefficients is equal to 23, and using the extended Euclid's algorithm, we can represent it as a linear combination of these two numbers. So the coefficients of these linear combination is minus 3 and 4. Now we can multiply this equation with minus 3. So if we multiply 23 with minus 3, this gives us minus 69, exactly what is needed. On the right hand side, we will have what was in the previous line times minus 3. And again, what was in the previous line times minus 3. So in this case, this is our x, this is our y. So x is equal to 9, y is equal to minus 12. Okay, so this is one particular solution, but it turns out in this case that there is also another solution. X is equal to minus 4 and y is equal to 5. So again, it is very natural to ask at this point how to find all possible solutions to a Diophantine equation, in case there is at least one solution, of course. So we are going to develop this method soon, but before doing this, let's prove the following auxiliary lemma, which is also called Euclid's lemma. So if n divides a times b, and also the greatest common divisor of a and n is equal to 1, then n necessarily divides b. Okay, so this is proved as follows. So since a and n, since their greatest common divisor is equal to 1, let's represent 1 as a linear combination of a and n. So assume that ax and y are the coefficients of these linear combinations. So we know that there are such integers x and y such that ax plus ny is equal to 1. And this x and y can be actually easily found by Euclid's algorithm. Okay, then let's multiply this equation by b. What we get is axb plus nyb is equal to b. Okay, now we know that AB is divisible by n, which means that AB can be represented as Kn. Now let's use the formula, let's use the previous equation. So B is equal to AXB plus NYB, but now we know that AXB is equal to NXK, right? Just because AB is equal to Kn. So what we see is that B is equal to n times xk plus yb. So indeed, n divides b, right? Which proves the lemma. Now let's go back to the question of how to find all solutions of a particular Diophantine equation. So assume that we have two integers a and b, such that their greatest common divisor is equal to d. Let's also represent a as dp and b as dq, and assume that y0 is a solution of a Diophantine equation ax plus by is equal to c. So it is a solution, meaning that ax0 plus by0 is equal to c. So this is just a true fact. Then the theorem states that any other solution to this particular Diophantine equation has the following form. So x in this solution is equal to x0 plus tq, where y is equal to y0 minus tp, where t is any integer. So once again, what we state here is there are actually two statements here. First of all, that for any t, by considering x0 plus tq and y0 minus tp, we get a solution. And the second statement is that any other solution has the following form. Okay, let's prove both these statements. So first of all, the first one. So in this case, let me recall that we have A equal to dp, B equal to dq, and we also know that x0, y0 is a solution. Okay, then consider any other solution, any other 2 points x and y defined by x0 plus tq and y0 minus tp. So this is our new pair xy. Okay, let's consider what happens if we compute a times this x plus b times this y. So this will be equal to x a times x0, this is this term, plus by0, this term, plus t times aq, which is this term multiplied by a, minus t times bp. Okay, so this gives us t times aq minus bp. Okay, so just by the fact that x0 and y0 is equal to c, we can replace this term by c. On the other hand, we know that aq is equal to bp. Okay, this is just because a is equal to dp and b is equal to dq. Okay, so this is just equal to 0. Okay, so this just cancels. So this shows that any x and y of this form is a solution. Okay, so what remains to be shown is that any other solution has the following form. So for this, let's just show that any two solutions are actually different by they differ as follows. So to get one solution from another one, we need to add tq to x and subtract tp from y. Okay, so for this, consider such two solutions, xy1, y1 and x2, y2. So we know that ax1 plus by1 is equal to c, and the same holds for x2, y2. So this means that we can subtract one from another, so this from the other one. This will give us the following equation: a times x1 minus x2 plus b times y1 minus a2, y2 is equal to 0. Okay, so this is our equation. Okay, so in this case, let's divide this equation by d. What we will get is the following. So a divided by d is equal to p, b divided by d is equal to q. So this is our new equation. Okay, now what we know is that the greatest common divisor of p and q is equal to 1. Okay, this allows us to conclude, since this is divisible by q and this is divisible by q, we know that this is divisible by q. On the other hand, p and q, the greatest common divisor of p and q, is equal to 1, which means that x1 minus x2 by the Euclid's lemma should be divisible by q, right? So we can represent x1 minus x2 by tq. This already shows us that the two x's are different by a multiple of q, right? And this is actually x1 minus x2 is equal to tq. And in this case, if we plug this tq into this equation, this will give us that the difference of y1 minus y2 is equal to minus tp. So exactly what we needed to prove, right? So this concludes the proof of this lemma that allows us to express all solutions to the Diophantine equations through some initial single solution. Okay, let's finally show an example of applying this lemma. So once again, in this case, we have 3 passes times 9, 3 bills of 3 passes. So this is 27 plus 5 is equal to, it should be minus 5 is equal to 22. Okay, it should be plus 5 times minus 1. Okay, so in this case, we are solving the following Diophantine equation: 3x plus 5y is equal to 22. And we know that there is a single solution, at least one solution to this problem, expressed as follows: x0 is equal to 1, x0 is equal to 9, y0 is equal to minus 1. Okay, let me also recall that in this particular case, a is equal to 3, b is equal to 5, and the greatest common divisor, denoted by d, is equal to 1. So in this case, the numbers p and q are also equal to 3 and 5. So p is just equal to a, q is equal to b, just because the greatest common divisor is equal to 1. So our theorem states that any other solution is expressed through our initial solution, which is as follows: 9 minus 1, as follows. It is 9 plus 5t, this is x, and y is minus 1 minus 3t. Okay, so this gives us the whole range of solutions. So for any integer t, this gives us a new solution. Okay, assume at the same time, recall that in our case we would like x and y, we would like x to be non-negative and y to be non-positive, actually, right? So in this case, this translates to the following set of inequalities. We would like 10 plus 5t to be at least 0, and we would like minus 1 minus 3t to be at most 0. Okay, so just by solving these two simple inequalities, we get that t should be at least minus 3. Okay, and since t must be an integer, this just means that t should be non-negative. So what we get in the end is that any solution x equal to 9 plus 5t and y equal to minus 1 minus 3t gives us a valid solution to our Diophantine equation. For example, by taking t equal to 10, you get a solution x is equal to 59 and y is equal to minus 31, which means that if you give 59 3-peso bills to the cashier and the cashier returns you 31 5-peso bills and 1 apple, this will be a fair trade. We conclude the lesson with another important application of the Euclid's algorithm, namely modular division, or inverses modular n. So for this, first recall the following multiplication table modulo 7. So it gives us, for any two remainders modulo 7, the remainder of their product modulo 7. For example, if you remind a number whose remainder modulo 7 is 5 with a number whose remainder modulo 7 is 3, then what you get is a number whose remainder modulo 7 is equal to 1. Okay? So a closer look at this table reveals the following property. In every row, except for the zeros row, we have all 7 different integers. For example, if we take a look at this row, it has all 7 different integers, as well as this row, as well as all other rows except for the zeros one. And this actually tells us the following important property. So for any non-zero a and for any b, we can always find a number x such that a times x is equal to b modulo 7. So in a sense, x here is b divided by a modulo 7. So let me illustrate this property on some toy examples. So if a is equal to 3, for example, and b is equal to 5, then what we're looking for is a number x such that 3 times x is equal to 5 modulo 7. So in a sense, what we're looking for is a column such that when intersected with the third row, we have a number 5. And this is the fourth column, so we have a number 5 here. So it tells us that if x is equal to 4, then we have the right congruence here. And indeed, 3 times 4 is 12, it is congruent to 5 modulo 7. And since all the integers are different in all the rows except for the zeros rows, such a division is always possible. Now let's consider another case when let's consider multiplication table modulo 6. So as you see, this property does not hold anymore for all the rows here. This in particular means that sometimes a division is possible and sometimes it is not. So for example, if you would like to find a number such that when it is multiplied by 5 it gives you a remainder 2 modulo 6, then what you are basically looking for is the number is the column such that in this row we have 4, So as you see, if you multiply 2 by 4, this gives you 10, and this is indeed 4 modulo 6. On the other hand, if you would like to find the number x such that when multiplied by 3 it gives you number 6, then you just cannot find such a number. So you cannot find one in this row. And it is actually clear why. Just because any number multiplied by 3 is always divisible by 3, right? So if you would like 3x to be congruent to 1 modulo x, then you essentially would like 6 to divide 3x minus 1. So if 6 divides 3x minus 1, then necessarily 3 should divide 3x minus 1. But 3x minus 1 cannot be divisible by 3 just because 3x is divisible by 3, and then we multiply a number 1 which is not divisible by 3. So as we see in this case, we cannot divide 1 by 3 modulo 6. More formally, we cannot find the number x such that 3x is congruent to 1 modulo 6. So at this point it is natural and it is important to ask in what cases we can divide by a. Okay? So let's first define the multiplicative inverse modulo n. So the multiplicative inverse of a modulo n is a number a bar such that a times a bar is congruent to 1 modulo n. So now it is important to understand that if we have a multiplicative inverse modulo n, then we can divide any number b by a in this case. Namely, we can always find a number x such that a times x is congruent to b modulo n. And such an x is just equal to b times a bar, where a bar is an inverse. So let me illustrate this. So for any number b, if we multiply such an x, which we defined as b divided by a, then this is b times a bar multiplied by a. But this is just 1, just by the definition of the multiplicative inverse. So if you multiply this x by a, you get b as desired, right? So if a has a multiplicative inverse, then for any number b, we can find the number x such that ax is congruent to b modulo n. Okay, so now it is important to understand when a has a multiplicative inverse. But before this, let's show that if a has a multiplicative inverse, then it is necessarily unique. Okay, this is actually easy. So if there are two different inverses, denote them by x and y, then we can write the following set of equations. So first of all, x is equal to x times 1. 1 is just a times the inverse of a, which is y, right? Now we have two multiplications and let's perform them in a different order. Let's first multiply x by a, and this is again 1 just because x is also a multiplicative inverse times y, and this is y. So what we've proved just is that x is equal to y. So if there are two multiplicative inverses of a modulo n, then they are equal. Okay? Now the question is when there is a multiplicative inverse of a modulo n. And the simple answer is that it exists whenever the greatest common divisor of a and n is equal to 1. Okay, so this is a simple criteria of the existence of the multiplicative inverse of a modulo n. So let's prove this. So first of all, the fact that ax is congruent to 1 modulo n actually is equivalent to the fact that ax plus kn is equal to 1 to some integer k, right? So this just means that ax minus 1 is divisible by n. So there is some number k such that ax minus 1 is equal to kn, some integer k. Okay? On the other hand, this can be considered as a Diophantine equation with these two coefficients a and n. And we know that there exists a solution for this Diophantine equation if and only if the greatest common divisor of a and n divides 1. So in our terms, this is c, and we have a and n as coefficients, and the greatest common divisor of these two coefficients should divide C. So C is 1 in this case. So for the greatest common divisor there is no choice, so it should be equal to 1. So the only number that divides 1 is equal to 1, which proves the theorem. Okay? So now we know that there is a multiplicative inverse of A and N, and if and only if the greatest common divisor of A and N is equal to 1. This actually also shows why there is no multiplicative inverse of 3 modulo 6 in particular. Okay? Now, so what this tells us is that if the greatest common divisor of A and N is equal to 1, then there is a multiplicative inverse of A modulo N, and this in particular means that we can divide by A modulo N. And we can actually do this algorithmically. We can implement an efficient procedure for doing this. So given numbers A, B, and N, we would like to find a number x such that AX is equal to B modulo N. That is, we would like to divide B by A. So to find a solution to such an equation, to find such an x, we can do the following. First, given A and N, we use the extended Euclid's algorithm to represent A as a linear combination of A and N. So it gives us the following two coefficients, T and S. So NT plus AS is equal to 1. So this means immediately that S is a multiplicative inverse of A modulo N. So indeed, if you multiply A by S, you get 1 modulo N, right? So because AS plus something divisible by N is equal to 1. So the remainder of AS is equal to 1 modulo N. So S modulo N, to be more precise, is a multiplicative inverse of A modulo N. Now it remains just to multiply B with S. Namely, recall that just dividing by A is the same as multiplying with the with multiplicative inverse of A modulo N. And as we've just discussed, it can be found by the extended Euclid's algorithm. Okay? Now let me conclude with a toy example. So assume that we would like to divide 7 by 2 modulo 9. First of all, we can do this just because the greatest common divisor of 9 and 2 is equal to 1. So since it is equal to 1, it can be represented using the extended Euclid's algorithm as a linear combination of 9 and 2. So in this particular case, 1 is equal to 9 times 1 plus 2 times minus 4. Okay? This tells us that minus 4 is a multiplicative inverse of 2 modulo 9. So minus 4 is actually 5 modulo 9. Okay, which means that to divide 7 by 2 modulo 9, it is sufficient to multiply 7 by 5 modulo 9. When we multiply 7 by 5 modulo 9, it gives us 8. So which means that 7 divided by 2 is equal to 8 modulo 9. So let's check it. Indeed, if we multiply 8 by 2, it gives us 16, and it is indeed 7 modulo 9. So indeed 8 is equal to 7 divided by 2 modulo 9. So what we've just presented is an efficient procedure for division modulo n and for computing inverses modulo n. And this is an essential step of modern crypto systems like RSA, which we will learn in the later lessons in this class.
Hi! In this and the next module, we're going to study cryptography. Cryptography, in simple words, is a science about sharing secrets in such a way that no one can learn those secrets other than the parties involved. But of course, all this is not just about childish games, and almost everyone uses some type of cryptography every day. For private communications via cell phone, email, messengers, for secure money transfers, for example to pay for an online course, for online commerce, for secure authorization in some online services such as social networks or Coursera, and for software installation, so that when you install some program on your computer, you can trust the provider of that software, and to check that this is actually the provider of the software, use a kind of digital signature, and that digital signature also uses cryptographic algorithms so that you can actually check that this is the trusted party who provided the software and not some malicious person who wants to install a virus on your computer. So the model we're going to use is that two parties, called typically Alice and Bob, want to securely communicate some secret information, but there is always someone who is trying to eavesdrop on that connection. For example, some secret agent called Mallory, or this person is typically called Eve in cryptography for eavesdropping, who taps on a wire or taps on the radio signal and tries to get the information which flows from Alice to Bob and back. But if we somehow make a cipher out of that information, we can hope that Mallory or Eve cannot decipher that information and get the initial message that Alice wanted to send to Bob, or vice versa. And a common way to do this that we all use is Alice and Bob should have some shared secret code, so that Bob, if he wants to transfer a message like "Hello Alice," he can encrypt this message using this secret code, and after encryption, this message starts to look like a sequence of random numbers and letters and bits, and nobody can understand what's there, and then Alice can decrypt this message using the same secret code, and then she can understand that Bob has just sent her a message, "Hello Alice." But there is a problem with this. The problem is, if you use the same secret code many times, people around can actually guess what it is. And some examples is from your childhood. For example, you maybe had a secret code with your friends when you just changed the words to their opposites, and you talked when there were some grown-ups using those opposite words, but then actually they were understanding what you're saying after a few minutes listening to your secret code. Another way is to replace some words with some other special words or rearrange letters. This is an example of an ancient Greek cipher called Caesar cipher. But all these can actually be broken using statistics if there are many examples of encrypted messages. And so you actually need to change your code pretty often. One significant example of this is what you could see in the movie called The Imitation Game about World War II, when the Nazis used a ciphering machine called Enigma, and it was very complex and had a very complex cipher, and more than that, they changed their code every day during the war. But the Allies, led by Alan Turing, could still break the cipher, because during the day the Nazis sent many messages encoded by the same code, and then Alan Turing basically invented a computer which could go through all possible combinations of the Enigma machine and try to decipher some of the intercepted ciphertexts. And if the resulting plaintext message looked like plain English, then it should be the code. Otherwise, it looked like still some random sequence of bits and letters and numbers, and so the computer went through all the possible combinations in a brute force, and at some day it was fast enough to recover the code. So, one should really use different code for each communication. But that can be a problem, because how do you even share the secret code itself? This is also some communication, and the eavesdropper can get this communication while he's listening. So what if you're communicating not just to a person standing next to you, but you're communicating from different continents, and you need a new code for each communication? What to do? So one solution for this from the cryptographic science is called public key cryptography, and we're going to study it in the next module. But the basic idea is that every party generates two keys, a public key and a private key. So both Alice and Bob have their own, Alice's public key and Alice's private key, and Bob also has a public key and a private key. And then, to send message, for example, from Alice to Bob, Alice can use Bob's public key, which is known to everyone. She uses this public key to encrypt the message. And then Bob uses his private key to recover Alice's message. And in that way, they share some information that only both Alice and Bob know, but no one else can know at all. And symmetrically, if Bob wants to send a message to Alice, he uses Alice's public key to encrypt this message. And this message can be Bob's private key. And then Alice can decipher this message using her private key. And then they both will know Bob's private key. And then they can use it for the regular cryptography with the secret code that I've shown you on one of the previous slides, which is called a symmetric cryptography. And then when they already have a shared secret code, no one can actually decipher the messages going back and forth between them, and that is already secure. So, cryptography is a science about sharing secrets in such a way that no one can eavesdrop or change your messages on your behalf so that no one notices. And this is used for authorization and for making sure a person cannot deny having sent the message. And billions of money transactions use encryption every day. And the particular kind of encryption that we're going to study in the next module, called RSA encryption, is arguably the most frequently used program in the world. So this module, we're going to study some tools for cryptography, some building blocks. And the next module, you're going to study actually the keys and the secure ciphers, and also how to break them if they're used incorrectly. Hi! In this lesson we're going to study integer factorization, prime numbers, composite numbers, and some of their properties that are useful for cryptography and for other building blocks for cryptography. And we're going to start with the prime numbers. If you look at this picture, you'll understand that it is possible to arrange 12 apples in a rectangle with several rows and several columns, so that there is more than one row and more than one column. And what do you think? Is it possible to do the same for 13 apples? So actually, if it was possible with some A rows and B columns, then 13 would be equal to the product of A and B, because this is the area of the rectangle. And you can check yourself by trying all the possible combinations that it is actually not possible for any A and B which are bigger than 1. So, for which integers n more than 1 is it possible to arrange n apples in a rectangle with more than one row and more than one column? So, if it is possible for some integer n, and there are A rows with B apples in each, then n is equal to the product of A and B. Also, we know that A and B have to be bigger than 1. So A and B in this case are divisors of n. And so n must have divisors other than 1 and n. And such n which have divisors other than 1 and n are called composite, and the others are called prime. And the definition of prime numbers is the following. A positive integer n bigger than 1 is called prime if it has no positive divisors other than 1 and n. And the examples of prime numbers are on the slide, starting from 2, 3, 5, 7, 11, and so on. And the composite numbers are starting from 4, which is equal to 2 times 2, 6, which is equal to 2 times 3, and so on. We have a bunch of even numbers up to 14, which is equal to 2 times 7, and then 15, which is 3 times 5, and so on. So we can always, what we call, factorize a number into a product of two other integers, which are bigger than 1. And what about 1? We didn't call it prime, we didn't call it composite. Well, actually, this is considered a special case, because from one point of view it has no divisors other than 1 in itself, but it is not considered prime. And it is not considered composite either, it's just a special case. And another special case is number 0. actually any number divides 0, because 0 times a equal to 0, so a is a divisor of 0 by definition, so it has an infinite number of divisors. However, it is also considered neither prime nor composite. So prime numbers have a lot of useful properties, which we're going to study and then use in the cryptographic algorithms. See you in the next video. Hi! In this video we're going to study how integers can be represented as products of prime numbers. So by definition, a composite number can be represented as a product of two smaller integers, like 1001 can be represented as a product of 7 and 143. And if one of the factors, like 7 and 143, are called factors of 1001, if one of them is not prime, then we can again represent it as a product of two even smaller integers. And indeed, 143 is not prime, it can be represented as a product of 11 and 13, and so in the end we get a representation of 1001 as product of 7, 11 and 13. And those three numbers, 7, 11 and 13, are already prime numbers, so we cannot continue this process of factorization. So the process of representing an integer as a product of smaller and smaller integers is called integer factorization. We could start with another representation of 1001 as a product of two smaller integers, like 1001 is equal to 11 times 91. But then 91 is not a prime number. It can again be represented as a product of two smaller integers, 7 and 13, and then in the end we get a representation of 1001 as a product of 11, 7 and 13. So this is another factorization. We can represent each way of factorization as a tree, where on top in the root we have our initial number 1001, and then on the first tree it first breaks in two branches. On the left the first factor 7, and on the right the second factor 143, and then we can also break 143 into two branches, into 11 and 13. And on the right factorization we start with the root 1001, then the left factor is 11 and the right factor is 91. And then 91 can be again broken into factors 7 and 13. And you can see that the integers in the leaves of this tree give a representation of 1001 as a product of primes. In the left tree it is the product of 7 by 11 by 13, if we read from left to right, and in the right tree is product of 11 and 7 and 13. And you can notice that the only difference between these two representations is the order of the prime numbers in the factorization. But these prime numbers are the same. And in the next videos we are going to study two questions. First is whether it is always possible to represent an integer as a product of primes, and another one is whether it is always a unique representation and two representations can only differ by the order of primes in them. Hi! So in this video we're going to understand whether a representation of integer as a product of primes always exists. And so there is actually a theorem that states that every integer bigger than 1 can be represented as a product of one or more prime numbers. Let's prove this theorem. So if some integer n is already prime, then we're good. It can be represented as a product of just this integer itself. Otherwise, n is composite, so by definition it can be represented as a product of two smaller numbers, a and b. Then if a and b are already prime, we're again good, because n equals to ab is a representation of n as a product of two primes. Otherwise, at least one of them is composite. For example, we can consider a without lots of generality composite. Then we can factor a into a product of two even smaller integers, a1 and a2. And it is key that both these integers are again smaller than a. And then we can continue this process of factorization while it is possible. And it is possible while there is at least one factor in the representation of n which is not prime. But we cannot continue this process indefinitely. It must stop, because all the factors get smaller and smaller, but they're also lower bounded by 1. They're all bigger, strictly bigger than 1. So this process must stop. And when this process stops, all factors are prime, because if one of the factors was not prime, we could continue factorization, but we cannot. So this process stops, and at that point we have some representation of n as a product of prime numbers. And to see it, for example, if we made just 2 steps in this particular factorization process, we started with n equal to ab, and then we factored a as a1, a2, and then it turns out that we cannot continue, that a1 and a2 and b are prime. Then we get the representation of n as a product of a1, a2 and b, and all those 3 numbers are prime. So we proved our theorem. And in the next videos we're going to understand whether such representation is in some sense unique. Hi! In this video we will start with the question of whether the representation of integers as a product of primes is unique, and we're going to prove Euclid's lemma, which will help us to answer this question. So first, let's consider this example when we have a very large number and it is represented as a product of 2 integers on the left and as a product of another 2 integers on the right. And these pairs of integers look like big prime numbers. So does it prove that there can be 2 completely different representations of the same integer as a product of primes? What do you think? Well, actually, if you try more and you try to factor those big integers, it turns out that those are not prime, and that all those 4 big integers can be further factored into products of numbers like 137 times 571 and 137 times 727 and so on. And you see that on both sides, on the left and on the right, we have the factor 137, and actually all these 3-digit factors are on both sides of the equation. And so in the end it turns out that we can actually represent our big number as a product of 4 numbers: 137, 337, 571 and 727, and these 4 are in the end prime numbers. And actually those initial 2 representations of n as products of 2 numbers are not prime factorizations, and this final representation is a prime factorization. And so it doesn't prove that there can be 2 different representations of n as products of primes. But it doesn't prove vice versa. It doesn't prove that it is always possible to represent n as a product of primes in a single way. And we're going to study this question further. But to help us, we're going to recall the following lemma, called Euclid's lemma, that if p is a prime number and p divides product of integers a and b, then p divides either a or b. Now let's go quickly through this proof. Let's suppose that this prime number p doesn't divide a. Then consider the greatest common divisor of a and p. This greatest common divisor divides p, so either it is equal to 1 or it is equal to p because p is prime. But we know that p doesn't divide a, so this greatest common divisor cannot be equal to p, and so it necessarily is equal to 1. And in this case, we proved in the previous module that multiplication by a modulo p is invertible, which means that there exists some integer x such that x times a is equal to 1 modulo p. And then, if p divides the product of a and b, it means that product of a and b is equal to 0 modulo p. Let's multiply both sides by x and conclude that x times a times b is equal to 0 modulo p. Then notice that x times a is equal to 1, so we can just cancel these 2 terms, both x and a, and get that b is equal to 0 modulo p. And if b is equal to 0 modulo p, then p divides b. So we proved our theorem. We proved that if p doesn't divide a, then p divides b. And we're also going to prove a corollary that if a prime number p divides product of several integers, then p p divides at least one of these integers. Indeed, if p divides some product of a1 times a2 times and so on times ak, we can represent this product of k integers as a product of two integers, a1 and the product of all the other integers from a2 to ak. So, by the previous lemma, by Euclid's lemma, either p divides a1 and we're already good, or p divides the product of all the other integers, a2 up to ak. And then we can again represent this product as a product of a2 and a3 through ak. And in the latter case, p divides either a2 or product of a3 through ak. And again, if it divides a2, we're good, otherwise it divides either a3 or product of everything else, and so on. So in the end we get that p is going to divide at least one of these several integers. And we're going to use this fact to prove that prime factorization of any integer is unique up to order of prime factors. Hi! In this video we're going to finally prove that the prime factorization of any integer is in some sense unique. So the theorem states that every integer n bigger than 1 can be represented as a product of one or more prime numbers, and any two such representations of the same integer n can differ only by the order of prime factors. Actually, we've already proven the first part, that the representation as a product of prime exists. Now let us prove the uniqueness of the representation. So first, assume that there can be two different representations of n as product of primes, which differ not only by the order of primes. So that n is equal to both p1 times p2 times and so on up to pk, where p1, p2 and so on up to pk are prime numbers, and also n is equal to q1, q2 and so on up to ql, where these q's are also prime numbers, and some of them are different from some of the p1, p2 and so on up to pk, because these two representations differ not only by the order of products but also by some of the factors. So if there are some common factors in these two representations, for example p1 is equal to q2, we can just cancel them until there are no common factors. So just remove these common factors from both the left part and the right part of the equality, and the equality will stay true. So now assume that this still holds true, there is nothing to reduce, and there are two different representations of the same integer n as product of primes without common factors. And again, they still differ not only by the order of the factors. Now we see that p1 times p2 up to pk is equal to q1 times q2 up to ql, and we know that the left part is a product of numbers which includes p1. So p1 is a prime number and it divides this left part. So it divides the right part of the equation. So p1 divides the product of q1, q2 and up to ql. And by the corollary from the previous video, we know that it follows that p1 divides at least one of the integers q1, q2 and up to ql. If p1 divides some qi for some I, then given that qi is also a prime number and p1 is a prime number, p1 might be a divisor of a prime number. It cannot be equal to 1 because it is a prime number and 1 is not considered prime, so p1 must be equal to qi. But this is a contradiction because we have just assumed that these are two representations without any common factors, and we just found a common factor p1 and qi. So, as we came to a contradiction, our assumption that there can be two different representations which differ not only by the order of factors for some integer n is false. And so actually any two representations can only differ by the order of the primes. And I want you to note that when we cancelled some of the factors, it didn't change the fact, because if we cancel two factors and then we return them back into the representation, well, that just changes the order of the factors, but this factor appears in both representations, so they don't start to differ in more than the order of factors. So we've just proven that factorization is unique up to the order of factors, and from this we can make some useful conclusions. For example, for any representation of n as a product of primes, we can sort these prime factors in ascending order and then group all the equal primes together. And then we can get what is called the canonical representation of integer n. N is equal to p1 to the alpha 1 times p2 to the alpha 2 and so on up to pk to the alpha k, where p1 is less than p2 and so on, and this is less than pk, and these are all the prime factors of n in ascending order, in strictly ascending order, and alpha 1, alpha 2 and so on up to alpha k are some strictly positive integers, the degrees in which these primes get into the representation of n as a product of primes. It follows from the unique factorization theorem that the canonical representation of any integer n bigger than 1 is unique, because if any two representations differed only by the order of prime factors and then we sorted these prime numbers in the ascending order, then the orders are already the same in any two representations after this sorting. And then if we just group the same primes together, well, we have the same number of the same prime factor in any two representations by the unique factorization theorem, so alpha 1, alpha 2 and so on up to alpha k will also be always the same for any initial representation. We can do it with another representation, so instead of just taking only prime factors of n which are divisors of n, we can actually take any set of primes, p1, p2 and up to pm, such that all prime divisors of n are in this set, but maybe some primes which are not divisors of n are also in this set, and then we can represent n as a product of p1 to alpha 1 times p2 to alpha 2 and so on up to pm to alpha m. And we can of course sort these numbers from the least p1 to the biggest pm. However, in this case, some alpha i's can be 0 exactly for those prime factors which are not divisors of n. Actually, we can do even more than that. In particular, we can take the set of all prime numbers and enumerate it from the smallest, starting from p1 equal to 2, p2 equal to 3, p3 equal to 5, and so on, and then represent integer n, any integer n bigger than 1, as a sequence alpha 1, alpha 2, alpha 3, and so on, the degrees in which these prime factors, from the set of all prime factors, get into the representation of n, where alpha I will be equal to 0 if some prime number pi doesn't divide n. Otherwise, alpha I is exactly the degree from the canonical factorization of n corresponding to this prime factor pi. In this representation, all integers have the same set of prime factors, although some of them get into degree 0. And this is a useful representation. For example, in this representation it is easy to multiply numbers. If we consider two integers m and n, and for integer m we have sequence of degrees alpha 1, alpha 2 and so on, and for integer n we have another sequence beta 1, beta 2 and so on, then the product of these two numbers mn corresponds to the sequence alpha 1 plus beta 1, alpha 2 plus beta 2 and so on. Why is that? Well, because when we multiply two numbers, then the prime factors from one number get added to the same prime factors of the second number. So if we sort them again in ascending order, and we grouped alpha 1 numbers p1, and then we grouped beta 1 numbers p1 for n, and then we group them together, we get just alpha 1 plus beta 1 copies of the same prime number p1. And so the degree of p1 in the product mn is equal to alpha 1 plus beta 1. And the same goes for p2, for p3, and so on. So it is easy in this representation to multiply any two numbers. However, there is no simple way to sum two numbers in this representation, because we don't know what will be the prime factors of m plus n, and we cannot say how to compute these prime factors and their degrees from just sequences alpha 1, alpha 2 and so on, beta 1, beta 2 and so on. So, in conclusion, now we know that any integer can be represented as a product of primes. any two such representations differ only by the order of prime factors, and there exists a canonical representation n is equal to p1 to the power of alpha 1 times p2 to the power of alpha 2 and so on up to pk to the power of alpha k, such that p1, p2 and up to pk are all the prime factors, all the prime divisors of n, and alpha 1, alpha 2 and so on up to alpha k are the degrees in which these prime factors get into the representation of n, and this canonical representation is totally unique for any integer n. And also, we can represent any integer n as a sequence of degrees for all prime numbers, starting from p1 equal to 2 and then 3, 5, 7 and so on, and we can represent n as a sequence, alpha 1, alpha 2 and so on, of degrees in which these prime numbers get into the representation of n, where all these alphas are non-negative and they're equal to 0 if the corresponding prime number doesn't divide n. Otherwise, it is bigger than 0. And in the next video, we're going to study some more useful conclusions from this unique factorization theorem. Hi! In this video we're going to draw some useful implications of the unique factorization theorem that we proved in the previous video. The first is some simple divisibility criterion that we now have. So when does m divide n if you know their prime factorization? And the answer is, if we consider canonical representations of both m and n, then m divides n when first all prime factors of m are among prime factors of n, and if pi is equal to qj, if prime factor of m corresponds to the jth prime factor of n, then it must be that the corresponding degree in which this prime factor goes into m is less than or equal to the degree in which this prime factor goes into the representation of n. So we can just compare the sets of prime factors of both numbers, and then we can compare the degrees of the corresponding prime factors. If the set of prime factors of m is a subset of the set of prime factors of n, and the corresponding degrees for m are less than or equal to the degrees for n, then m divides n. Another question that we want to answer easily is when numbers m and n are coprime, and integers m and n are called coprime is their greatest common divisor is equal to 1. And given canonical representations, that is again easy to say that m and n basically don't have any common divisors, and in particular they don't have any common prime factors, and so greatest common divisor of m and n is equal to 1 if and only if there are no common prime factors between prime factors of m and prime factors of n. So we just compare the sets of prime factors in the canonical representations, and if those sets don't intersect, then numbers m and n are coprime. Another question is how to compute the greatest common divisor itself, in case it is maybe not equal to 1. So let set of numbers p1, p2 and so on up to pk be all the prime divisors of m and n, both of them, not just one of these numbers, but the union of the sets of prime factors of both these numbers. Then we can represent both numbers m and n as products of these primes in some degrees. Note that some of these degrees, alpha I and beta I, can be equal to 0 in this case, but still we can represent them both as products of the same primes in some different degrees. And then what we need to take is, in each column, we need to take this prime in some degree, and this degree must be less than or equal to the corresponding degree in both m and n, because this number must divide both m and n, and we just learned the divisibility criterion, that the degree of the prime factor in the number that divides another number should be less than or equal to the corresponding degree in the number it divides. So for the greatest common divisor that divides both m and n, the degrees must be less than or equal to the degrees in both m and n. But this is the greatest common divisor, so this should be the greatest degrees which still satisfy this property. And these are the minimums of the corresponding alpha I and beta I. So greatest common divisor of m and n is just product of p1 to the power of minimum of alpha 1 and beta 1 times p2 to the degree of minimum of alpha 2 and beta 2, and so on. Because these minimums are less than the corresponding alpha I and beta I, and these are the greatest degrees possible, which are less than both alpha I and beta I. So, note that computing greatest common divisor is actually algorithmically much easier than prime factorization. Computing greatest common divisor can be done with Euclid's algorithm that we learned in the previous module, and still no efficient algorithm is known for prime factorization. So you shouldn't actually try to do prime factorization to compute GCD. It is just convenient to know how to compute GCD given prime factorization, because it can lead to some other useful conclusions, but if you want to actually compute GCD, you should use Euclid's algorithm. It is fast and pretty simple. Another useful function of two numbers is called least common multiple. It is very similar to the greatest common divisor, but in some sense it's vice versa. So the least common multiple LCM of AB of two integers a and b is the smallest positive integer x such that both a and b divide x. So now let's consider some examples. Least common multiple of 1 and 10 is 10, because 10 divides 10 and 1 divides 10, and of course 10 is a common multiple of both 1 and 10, but any number less than 10 cannot be the LCM, because 10 must divide it, and so it must be at least 10. And for 2 and 3, the smallest number such that both 2 and 3 divides it is 6, because 2 doesn't divide 3, 3 doesn't divide 4, 2 doesn't divide 5, and now 6 is the least common multiple because both 2 and 3 divide 6. And two other examples is least common multiple of 2 and 4 is 4, because 2 divides 4, and in the case when A divides B, the least common multiple is just B. And the least common multiple of 4 and 6 is 12. So now, how to compute LCM in the general case. So let's again consider all the prime factors of both m and n, p1, p2 and up to pk, and then represent both m and n as products of these prime numbers in some degrees, some of which can be 0. Then the least common multiple must be a number that both m and n divide, and so it must contain all these prime factors. It doesn't need to contain any other prime factors, because then it won't be the least common multiple. And now we only need to determine which degrees of these prime factors do we need. So these degrees must be greater or equal to the corresponding degrees in both m and n, so that both m and n divide this number. So we can just take the maximums of alpha I and beta I and take pi in these corresponding degrees, and that will be the least common multiple. So this formula is very similar, as you can notice, to the formula for greatest common divisor. We just replace minimum with maximum. Now, note that for any alpha and beta, minimum of alpha and beta plus maximum of alpha and beta is just equal to the sum of alpha and beta. And so, if we multiply the corresponding factors in the GCD and LCM, p1 to the degree of minimum of alpha 1 beta 1 times p1 to the degree of maximum alpha 1 beta 1, we will get p1 to the sum of alpha 1 and beta 1. And this is important because if we now represent m and n as products of this set of primes from p1 to pk, and we also represent GCD and LCM as products of these primes in the corresponding minimum and maximum degrees, then we will notice that the product of mn is product of these pi in the degrees of alpha I plus beta I, and also the product of GCD and LCM will be equal to the same number, because minimums and maximums, when we sum them up, this is the same as if we summed up alpha I and beta I, and so the product of GCD and LCM for two numbers is equal to their product. And this, in turn, gives us a way to quickly compute LCM. Because we already know that to compute GCD we can use Euclid's algorithm, and now LCM can be represented as a mn divided by GCD. So we can easily compute the product of two numbers, then we compute GCD using Euclid's algorithm, and then by dividing those two we can get the least common multiple. So now we have some useful conclusion from the prime factorization, although we don't need prime factorization itself to compute either GCD or LCM. From this presentation we concluded with a fast algorithm to compute LCM, which we didn't know before. So another lemma that we're going to use in the next lectures is that if A divides N and B divides N and A and B are co-prime, then their product divides N. So to prove it, consider all prime factors of A and B. So all prime factors of A are among prime factors of N, and degrees of those factors in N are bigger or equal to the corresponding degrees in A. The same goes for B. And also, as GCD of A and B is equal to 1, A and B don't share prime factors. We learned that in the beginning of this video. So now we can say that all prime factors of both A and B are in N. They don't intersect, so all the prime factors of their product are also in N. And the degrees in which they represent AB are also less than or equal to the degrees in which they represent N. So AB divides N necessarily. And in conclusion, using the unique factorization theorem, we made an easy criterion for divisibility of two numbers given their prime factorizations. We characterized co-prime numbers, that they don't share prime factors. We can compute GCD and LCM using prime factorizations. However, prime factorization is a hard problem and Euclid's algorithm is fast. So actually we need to use Euclid's algorithm to compute GCD, and given that GCD times LCM is equal to the product of the numbers, we can also compute LCM from Euclid's algorithm and by computing mn and dividing by GCD. And we know now that if two co-prime numbers divide some integer n, then their product also divides integer n. Hi! In this lesson we're going to study Chinese remainder theorem. It is called so because the Chinese mathematicians were able to prove this theorem approximately 2000 years ago, and it is concerned with remainders modulo different numbers. So first we're going to study the remainders modulo some numbers and their properties. When remainder modulo one number defines remainder modulo another number, and when the remainders modulo two numbers a and b are completely independent and we cannot say anything about one remainder given another one. So first let's look at first few integers n and their remainders modulo 4 and 2. If we go from 0, we see that remainder of 0 modulo both 4 and 2 is of course 0. For 1 the remainders are both 1. For 2 the remainder modulo 4 is 2 and modulo 2 is 0. And then we get 3 and 1, then 0 0 again, 1 1, 2 0 and 3 1. And from these three rows we can conclude that probably the remainder modulo 4 completely defines the remainder modulo 2. Indeed, if two integers n1 and n2 have the same remainders modulo 4, if n1 is equal to n2 modulo 4, then it means that 4, by definition, divides the difference between n1 and n2. And as 2 divides 4, 2 also divides this difference between n1 and n2, and so n1 is equal to n2 modulo 2, and so their remainders are also the same. This means that indeed the remainder modulo 4 defines remainder modulo 2. And in particular, if the remainder modulo 4 is equal to 0 or 2, then the remainder modulo 2 is equal to 0, and if the remainder modulo 4 is 1 or 3, then the remainder modulo 2 is equal to 1. Now let's consider another example of remainders modulo 3 and modulo 2. Again, we go from n equals to 0, and the remainders are 0 0. For 1 they are both 1, then 2 0, 0 1, 1 0 and 2 1. And so now we see no correspondence. Basically, n modulo 3 doesn't define n modulo 2, and more than that, all pairs of remainders are possible. So we can see 0 0 and 0 1, 1 0 and 1 1, 2 2, 0 and 2, 1. These are all possible pairs of remainders modulo 3 and modulo 2, because there are only 3 values for remainder modulo 3 and 2 values for remainder modulo 2. So one remainder doesn't give any information about another. So now let's recall the divisibility criteria from one of the first modules of this course. Divisibility by 2 criteria is easy: that the last digit is even, then number is even, otherwise number is odd. Divisibility by 5, that the last digit is either 0 or 5, then it is divisible by 5, otherwise it is not. And the last digit is the remainder after division of n by 10. So 10 is equal to 2 times 5, and this is why the divisibility criteria by 2 and 5 are defined by the remainder modulo 10. So we get remainder modulo 10, and it defines remainders modulo 2 and 5, and in particular, if the remainder modulo 10 is 0, then the remainder modulo 2 and 5 are also 0, so this is why the last digit is what is important for divisibility by 2 and 5. And for example, for divisibility by 3, the criterion is completely different. It's about the sum of digits. If the sum of digits is divisible by 3, then the number is divisible by 3, otherwise it is not. And so it is not determined just by the last digit, and actually it is independent of the last digit. So whether we know or we don't know the last digit, which is the remainder of division of n by 10, it doesn't give us any information about divisibility by 3. So what happens in the general case, when one remainder defines another and when it doesn't give any information? So first, we want to prove this general lemma that if n1 and n2 have the same remainders modulo some number b, and a divides b, then n1 and n2 have the same remainders modulo a. In other words, if a divides b, then remainder modulo b defines remainder modulo a. And to prove it, first we know that if n1 and n2 have the same remainders modulo b, then n1 is equal to n2 modulo b, and so b divides the difference between n1 and n2. b divides this difference, and a divides b, so a divides this difference between n1 and n2. And so a divides n1 minus n2, it means that n1 is equal to n2 modulo a. And this is what we wanted to prove. So now let's consider the following problem. If n is equal to 1 modulo 6, then what can we say about n modulo 4? So we see that 4 doesn't divide 6, so the remainder modulo 6 doesn't define 4. But maybe we can say at least something. Maybe there is some dependence of remainder modulo 4 on the remainder modulo 6. Indeed, if n is even, then the remainder modulo 6 can only be 0, 2 and 4. You can check it yourself. And so if n is even, then the remainder modulo 6 cannot be 1. Okay? So if n is odd, then n modulo 4 can be either 1 or 3. And so if n is equal to 1, then n is both 1 modulo 6 and n is 1 modulo 4. So it is possible that n is equal to 1 modulo 6 and it has remainder 1 modulo 4. And if n is equal to 7, then again n is equal to 1 modulo 6 and n is equal to 3 modulo 4. So it turns out that n modulo 4 can be either 1 or 3 if n modulo 6 is equal to 1. So if we know the remainder modulo 6, we can make some conclusion about the remainder modulo 4, but we cannot define it uniquely. We can say that it can be either 1 or 3. It definitely cannot be 0 or 2. So there is some information in the remainder modulo 6 about the remainder modulo 4. And again, we want to understand what is the dependence. So the remainders modulo 4 and 6 are dependent. And actually, this is because 2 is their common divisor. And in general, if there is some d that divides both a and b, then the remainders modulo a and b are dependent, because the remainder modulo a defines remainder modulo d, and remainder modulo b also defines remainder modulo d. So they have to correspond to one another, and there is some dependence through the remainder modulo d. And it turns out that if a and b don't have any common divisors, if their greatest common divisor is 1, then the remainders modulo a and b are completely independent. And we're going to prove it in the next video, and this is what Chinese remainder theorem is all about. Hi! In this video we're going to prove Chinese remainder theorem about the dependence between remainders modulo coprime numbers a and b, and we'll give a constructive proof which will in turn give us an algorithm to use this theorem in practice to build some numbers with given remainders modulo a and b if we want them. So the theorem itself states that if a and b are coprime, then for any remainder Ra modulo a and any remainder Rb modulo b, there exists some integer n such that n has remainder Ra modulo a and remainder Rb modulo b. Also it says that if there are two such integers n1 and n2, then their remainders modulo product of a and b are the same. So in other words, we can consider all ab possible remainders modulo the product of a and b, 0, 1, 2 and so on up to ab minus 1. Every such remainder corresponds to a pair of remainders Ra and Rb. Ra is the remainder of R modulo a and Rb is the remainder of R modulo b. So we claim that if we consider pairs corresponding to each such R from 0 to ab minus 1, then each of the possible ab pairs Ra, Rb appears there exactly once, corresponds to some remainder R. So let's prove the first part, that if n1 and 2 correspond to the same pair of remainders, then their remainders modulo ab are the same. This is the easier part. So first we know that n1 and n2 both have remainder Ra modulo a, and from this it follows that n1 is equal to n2 modulo a, so a divides the difference between n1 and n2. Similarly, we can conclude that b divides the difference between n1 and n2. And also we know that a and b are coprime, and from the theorem we proved in the previous lesson, we know that if two coprime numbers divide some number, then their product divides the same number. So AB divides difference n1 minus n2. And this means in turn that n1 is equal to n2 modulo AB. So indeed the remainders of n1 and n2 modulo AB are the same. So we proved the second part of the theorem, that actually means that different remainders modulo AB lead to different pairs Ra, Rb. And this already actually proves the first part of the theorem. Indeed, the number of remainders R modulo AB is AB, all the numbers from 0 to AB minus 1, and the number of possible pairs of remainders Ra, Rb is also A times B, because there are A possible remainders modulo A and B possible remainders modulo B, and all pairs of them are possible. So each R corresponds to unique pair Ra, Rb. We just proved it because if two numbers have the same pair of remainders Ra, Rb, then their remainders modulo AB are the same. So if two numbers between 0 and AB minus 1 have the same pair of remainders modulo A and B, they have to coincide. So each R between 0 and AB minus 1, which is a remainder modulo AB, actually corresponds to unique pair. And the number of pairs is equal to the number of remainders. So each pair also corresponds to unique R. For each pair there has to be some remainder R that corresponds to it. Otherwise the quantities don't come out equal. So we will also show a constructive proof. This proof just says that, okay, for any Ra, Rb there is some remainder R which corresponds to this pair, but we don't know how to find it, and we want some algorithm that will find it for us to use in applications. So again, the greatest common divisor of a and b is equal to 1, and so it follows from the extended Euclid's algorithm from the previous module that 1 can be represented as sum of a times x plus b times y for some integer x and y. From this it follows that ax is equal to 1 modulo b and by is equal to 1 modulo a from this equality. So these two equalities already give us some pairs of remainders. In particular, ax corresponds to pair of remainders 0 and 1, because a divides ax, so remainder of ax modulo a is 0, and remainder of ax modulo b is 1 because ax is equal to 1 modulo b. Similarly, by corresponds to the pair 1, 0. So we have pairs 0, 1 and 1, 0. And from those pairs we can combine to get any pair we want. If we want pair RA, RB, then we can just combine pair 1, 0 with coefficient RA with pair 0, 1 with coefficient RB and sum them up, and we will get exactly pair RA and RB. Let's check that. So consider n, which is equal to RA times BY, because BY corresponds to pair 1, 0, plus RB times pair AX, because AX corresponds to 0, 1. So consider such n. And first let's see what is the remainder of this n modulo a. So n is the sum of two numbers, and the second number, RB times A times X, is divisible by a. So it is equal to 0 modulo a. So we only need to look at the remainder of RA times B times Y modulo a. And also we know that BY is equal to 1 modulo a, so we can just cancel the terms B and Y, and only RA remains. So n is indeed equal to RA modulo a. Now let's consider n modulo b, and similarly the first summand in the sum of these two terms, RA times B times Y, is divisible by b, so it is equal to 0 modulo b. And then RB times A times X is equal to RB, because A times X is equal to 1 modulo b, so we can just cancel AX and only RB returns. So indeed, this particular n has pair of remainders RA, RB, corresponding to modulo A and modulo B. And this gives us an algorithm to build integer n with the given pair of remainders modulo A and modulo B. The algorithm is the following. We take numbers a and b and we launch the extended Euclid's algorithm to represent their common divisor 1 as a sum of ax and by for some integers x and y. And now we know these x and y. And then to compute n, which has remainders RA and RB modulo A and B correspondingly, we just compute RA times BY plus RB times AX, and we get the n we need. So this is our algorithm again. What about the case when you have 3 modules, or maybe more modules? So for the case of 3 modules, it turns out that if all pairs AB, AC and BC are coprime, then remainders modulo A, B and C uniquely determine remainder modulo their product ABC. And to see that, we can first combine remainders modulo A and B to get remainder modulo AB. Then we can notice that if all pairs are coprime, then in particular AB is coprime with C. Why is that? Well, if A and C are coprime, then we know that they don't share any prime factors by the unique factorization theorem. If B and C are coprime, then B and C don't share any prime factors by unique factorization theorem. And then if we multiply A and B, it gets only prime factors from A and from B. So A and B don't share prime factors with C, so AB also doesn't share any prime factors with C. So AB and C are again coprime, and we can apply the same Chinese remainder theorem for numbers AB and C. We already get some remainder modulo AB, and we need some remainder modulo C. We just combine them to get a number with some remainder modulo product of AB and C, which is ABC. So this not only proves that the remainders modulo 3 numbers which are pairwise coprime are independent, this also gives us a particular algorithm to build a number with any given remainders modulo A, B and C. We just successively find first such n modulo first pair modulo A, B, and then we combine AB with C to get n modulo ABC. And if we get even more modules, we can also go pair by pair. For example, we have 4 numbers A, B, C and D. We first combine A and B, get n modulo AB. Then we combine AB with C and get n modulo ABC. And then we combine ABC with D and get n modulo ABCD, and so on. So it doesn't matter how many modules we have. If every pair of them is coprime, we can apply Chinese remainder theorem in a few steps and get any combination of remainders modulo each of these numbers. Actually, One of the applications of this Chinese remainder theorem is optimization of computations with very large integers. So instead of working with large integers themselves, we can work with their remainders modulo several big prime numbers. Because if some very large integers n1 and n2 are between 0 and product of many smaller prime numbers p1, p2 and up to pk, and their remainders modulo each prime number are the same, then these numbers also have to be the same by the Chinese remainder theorem, because any two different prime numbers are, of course, coprime. And if we define two integers which have equal remainders modulo this set of prime numbers which are coprime, then their remainders modulo the product of these prime numbers also have to be the same by the Chinese remainder theorem. So the remainders of n1 and n2 modulo p1, p2 up to pk are equal, but also both n1 and n2 are themselves less than this product. So they are themselves these remainders, so they have to be equal. So in this form, if we represent each integer n, instead of just being this large integer itself, we can represent it as a set of remainders of the integer modulo p1, p2 and up to pk, which are smaller. And in this form, it is fast to sum and multiply integers, because we can just sum and multiply the corresponding remainders modulo p1, p2 and so on up to pk. But it is hard to compare which number is bigger. But if we don't need to compare, we just need to sum, multiply and maybe compare for equality, not for which one is bigger, then this is actually used in practice to speed up computations. So, in conclusion, we understand that remainder modulo n uniquely determines remainder modulo any divisor of n. And remainders modulo two different numbers a and b are independent if and only if a and b are coprime. And remainders modulo coprime numbers a and b uniquely determine the remainder modulo their product. And we also have an algorithm for constructing remainder modulo product of numbers given remainders modulo coprime numbers a and b. And it extends to more modules if every pair of modules is coprime. And this is one of the crucial building blocks in our future algorithms for cryptography. And in the next lesson, we're going to study another operation called modular exponentiation and its properties. Hi! In this lesson, we're going to study the operation of modular exponentiation. This operation is central for public key cryptography that we're going to study in the next module. Its properties allow for fast encryption and decryption for Alice and Bob, and it is easy for them in one direction, but it is hard to reverse for Eve, who doesn't know something that either Alice or Bob knows. So first we're going to study how to compute this modular exponent quickly in this video, and then in the next videos we're going to study the key properties that make it useful for encryption and decryption. So modular exponentiation is the operation of computing b to the power of e modulo m. So we need to compute number c, which is equal to b to the power of e modulo m. And how to do that? Well, there is no need to actually compute the possibly giant number b to the power of e and then divide it by m to get the remainder. Instead, we can just start with 1 and then multiply this number, which is at first 1, by b, immediately take the result modulo m, then multiply the result by b, and again take the result modulo m, and so on, and repeat all this e times, and we will get the remainder of b to the power of e modulo m because of the properties of remainders. Basically, the remainder of product is equal to the product of remainders, and this is the main property we are using here. So, for example, if b is equal to 7, e is equal to 4, m is equal to 11, basically we need to compute b to the power of 4 modulo 11, and we start with assigning value of 1 to c, And then we want to 4 times multiply this c by 7 and take modulo 11. So first we get 1 times c, which is equal to 7, and it has a remainder of 7 modulo 11. In the next step, c already has value of 7. We multiply 7 by 7, get 49. 49 is 44 plus 5. 11 divides 44, so the remainder is 5. On the next step, c has value of 5. We multiply 5 by 7, get 35. It is 33 plus 2, so the remainder is 2. And finally, the c already contains value of 2. We multiplied it once more by 7, we get 14, and the remainder modulo 11 is 3. And finally, we conclude that b to the power of e modulo m, which is 7 to the power of 4 modulo 11, is equal to 3. So this is the basically straightforward algorithm to compute modular exponentiation. We just start with assigning 1 to value of c, and then we repeat e times c is equal to c times b modulo m. And that's the whole algorithm. So we need just e multiplications, and that's fast enough, right? Well, not always. What if b, e, and m are actually integers with thousands of digits? And this is actually a practical case for cryptography. We need to work with really large integers so that if cannot decipher our messages. If b, e, and m are very small, then it would be very easy for if to decipher. But if we want our algorithm to work, then these numbers must be very big, and then making e multiplications where e is a number with 1000 digits, well, it won't finish in our life or probably in the time of existence of this universe, so we have to come up with something much faster than e multiplications. So can we actually do faster? Well, let's first consider the case when e is a power of 2. E is equal to 2 to the power of k. What we can do then? Well, on this example, when b is again equal to 7, but e is equal to 128, which is 2 to the power of 7, let's see what we can do. So first we can compute 7 to the power of 1, which is just 7, and then we can proceed with what is called squaring. So instead of computing powers of 7 as second power, third power, fourth power, and so on, we're going to square each time. So first we compute 7 squared, which is equal to 7 times 7, which is 49, and modulo 11 is equal to 5. Then, given that 7 squared is equal to 5 modulo 11, we're going to compute 7 to the power of 4 as product of 7 squared times 7 squared, or square of 7 squared. It is equal to 5 times 5, which is equal to 25, which is equal to 3 modulo 11. And on the next step, we're going to compute 7 to the power of 8, given 7 to the power of 4 equal to 3. So we are going to square this 7 to the power of 4, get 3 times 3, which is equal to 9 modulo 11, which is just 9. And again, we're going to compute 7 to the power of 16 by squaring 9 and get 4, compute 7 to the 32 by squaring 4 and get 5, then 7 to the 64 by squaring 5 and get 3, and then finally 7 to the 128 by squaring 3 and getting 9. So actually we made just 7 multiplications to compute 7 to the power of 128 instead of 128 multiplications. That's significant improvement. And in the general case, the algorithm looks like following. We start with assigning value of b modulo m to c, and then we repeat k times c assigned to c squared modulo m. And in the end, this c will be equal to b to the power of 2 to the power of k, which is equal to b to the power of e modulo m if e is in the form of 2 to the power of k. So instead of e multiplications, in this case we need just k, which is equal to binary logarithm of e multiplication, which is much faster with large e. For example, if e contains 1000 digits, then k will be just on the order of a few thousand, not a number which is itself has 1000 digits, but just on the order of 1000, and we can allow 1000 multiplications, of course, or maybe a few thousand. So what if e is not a power of 2? What then can we do? Let's consider a following example. So we already know how to compute powers of 2 of b modulo m. b squared, b to the 4th, b to the 8th, and so on. So how to compute b to the power of 13 modulo m then? Well, we can notice that 13 can be represented as sum of several powers of 2, because we know that any number can be rewritten in its binary form, and so any number can be represented as a sum of the powers of 2. And then b to the power of 13 is just product of b to the power of 8 times b to the power of 4 times b to the power of 1. So this is the idea of how we can actually compute b to the power of 13, although 13 is not a power of 2 itself. So in this example, we represent e as a sum of powers of 2, and then we compute this table of b to the power of 1, b to the power of 2, b to the power of 4, b to the power of 8, all the powers of 2 which are less than or equal to 13. We do this with the squaring algorithm from the previous, and we know all these remainders are correspondingly 7, 5, 3 and 9, and then we only need to multiply some of these remainders. In this case we need to multiply the remainders for b to the power of 1, b to the power of 4 and b to the power of 8, which is 7 times 3 times 9. 7 times 3 is 21, which gives remainder 10 modulo 11, and then 10 times 9 gives a remainder 2 modulo 11, and then in the end we conclude that b to the 13 modulo m is equal to 2. So what we do in this case is we rewrite e in binary form. We compute b to the power of 2 to the power of k modulo m for all powers of 2 which are less than or equal to e. And then we multiply together the results for all powers of 2 in the binary representation of e. So first we spend binary logarithm of e multiplications to compute all the b to the powers of 2 which are less than e, and then additionally at most binary logarithm of e multiplications to compute b to the power of e modulo m itself by multiplying all the needed b to the 2 to the kth modulo m for all to the kth which are in the binary representation of e. So in total we will do at most 2 times binary logarithm of e multiplications. And to conclude, modular exponentiation can be computed using at most 2 binary logarithms of e multiplications instead of just e multiplications. And for numbers e which have thousands of digits, this is just a few thousand instead of a huge number with 1,000 digits itself. To do that, we represent e in binary form, we compute b to the 2 to the power of k for all powers of 2 less than or equal to e using squaring, and then compute finally b to the power of e modulo m as a product of all needed b to the 2 to the power of k using binary representation of e. And in the next videos we are going to study the useful properties of modular exponentiation operation which allow us to safely encrypt and know that Eve probably won't be able to decrypt our cipher in any reasonable time. Hi! In this video we are going to prove Fermat's little theorem. This theorem is a key result for cryptography using modular exponentiation operation. This is also a key result for fast algorithms testing whether a large integer is prime or not, and it can also be used to make modular exponentiation even faster than what we came up with in the previous video, and I'm going to show you this in the end of this video. So the statement is pretty simple. If a prime number p doesn't divide some integer a, then a to the p minus 1 is equal to 1 modulo p. Let's prove this theorem. Consider all p minus 1 non-zero remainders modulo p, 1, 2 and so on up to p minus 1. So multiplying any such non-zero remainder by a is invertible, since p doesn't divide a, so the new remainder will also be non-zero. So we can actually build a graph on non-zero remainders, and we draw an edge from non-zero remainder r to a times r, where a times r is corresponding to the remainder of ar modulo p. And in such graph, all incoming and outgoing degrees are 1. Well, outgoing degrees are 1 because we only draw an edge from any r to a times r, this is just one edge, and the incoming degrees are 1 because the multiplying by a is invertible. And so if there is some edge from somewhere to ar, then it is only from r. We can just revert this multiplication by a to get r back. So this is a particular kind of a graph where all incoming and outgoing degrees of vertices are all equal to 1. So now let's see what happens if we start with some remainder r, multiply it by a, take remainder modulo p, and repeat this many times. What will happen? So in this graph we start with the vertex corresponding to remainder r, then we go to the vertex which corresponds to a times r. From there we will go to the vertex corresponding to a squared times r, then to the a cubed times r, and so on. We're going to repeat this for some time, but at some point we have to return to some vertex where we've already been, because there's only a finite number of such vertices, only p minus 1. So what if we return, for example, to this vertex? I claim that this cannot happen. Why is that? Well, because in this case this vertex would have incoming degree of 2. And we know that all the incoming degrees of all vertices are equal to 1, and so this is actually not possible. And so the only case in which we can return and not break this property that any incoming degree is 1 is if we return to the initial vertex. So we get a cycle which starts from r, goes to ar, a squared r, and so on, and after some l iterations it returns to the same vertex r. What this means is that by multiplying r by al times, we return to r. And this in turn means that a to the power of l multiplying by a to the power of l doesn't change anything, so a to the power of l is equal to 1 modulo p. Now let's consider what would happen if we started with some different remainder r prime. First we will go to a times r prime, then to a squared r prime, then to a cubed r prime, and so on, and then, as we already know, at some point we will get a cycle. And the length of this cycle has to be the same, because we already know that a to the power of l is equal to 1 modulo p, a to any smaller degree is not equal to 1 modulo p, and also we know that these two cycles won't intersect. So they either are two same cycles or they don't intersect, because if they intersect by some one vertex, this vertex will have incoming degree more than 1. It will have an incoming degree from first cycle and incoming edge from the second cycle. So this is not possible. Either two cycles coincide completely or they don't intersect. And this is key to prove the Fermat's-Little theorem. So we know that starting with any remainder r, we get the cycle of some length l. And then we conclude that this means that a to the power of l is equal to 1 modulo p. And starting with any other remainder r prime, we also get a cycle of the same length l. And also these cycles don't intersect, and these cycles in total contain all p minus 1 non-zero remainders, because we can start with any non-zero remainder, and some cycle will contain this particular remainder. So if there are exactly c cycles for some c, then c times l is equal to p minus 1, because each cycle has length of l, it contains l remainders. There are c cycles, they don't intersect, so in total they contain c times l remainders. And from the other hand, there are exactly p minus 1 non-zero remainders, and all of them are in the cycle. So c times l is equal to p minus 1. And then a to the power of p minus 1 is equal to a to the power of c times l. This we can rewrite as a to the power of l and all of this to the power of c. We know that a to the power of l is equal to 1 modulo p, so this is equal to 1 to the power of c, and 1 to the power of c is still equal to 1 modulo p. So we proved that a to the p minus 1 is equal to 1 modulo p. And this can be used for optimizing further modular exponentiation. Indeed, for a number a such that p doesn't divide a, we know that a to the power of p minus 1 is equal to 1 modulo p, and from this it follows that for any integer n, a to the power of n is equal to a to the power of n modulo p minus 1 modulo p, because any p minus 1 multiplications by a result in multiplying by 1, so instead of making many useless multiplications by groups of p minus 1, we just compute the remainder of n modulo p minus 1 and do this number of multiplications by a, and then we get the same remainder modulo p. And if number a is such that p divides a, then a in any power will be equal to 0. And so this property that a to the power of n is equal to a to the power of n modulo p minus 1 modulo p still holds. So actually for any integer a and any integer n, a to the power of n is equal to a to the power of n modulo p minus 1 modulo p. And it means that instead of computing very large powers of a modulo p, we can compute only powers which are up to p minus 1. And if we need to compute some power which is even bigger, we first divide this power by p minus 1, compute the remainder, and then compute the corresponding power of a. Hi! In this video we're going to study Euler's totient function. This is a key function for the RSA encryption, which we're going to study in the next module. It is easy to compute if factorization of integer n is known, and no fast algorithms are known to compute it if factorization of n is unknown. And no fast algorithms are known for factorization of integers. And this is actually why we can use it to do some cryptographic algorithms, because we want functions which are easily computable if we know something, but which are very hard to compute if you don't know this secret. So this is the main foundation of cryptography. The foundation of cryptography, it basically is not in something we can do very well, but in something we cannot do well. And integer factorization is a problem for which humanity currently don't know any fast algorithms. And this is why we can cipher something and then be almost sure that no one can decipher it unless this someone actually knows how to factorize big integers fast. For our knowledge, no one knows how to do that, and this is what allows us to do cryptography. So, what is Euler's totient function? It just counts integers between 0 and n minus 1, which are coprime with n. So phi of n is the number of such coprime integers between remainders modulo n. Let's consider some examples. For n equal to 1, 0 is coprime with 1, so phi of 1 is 1. Well, it is actually a special case of whether 0 is coprime with 1 or not, because, you know, every integer divides 0, and what does it mean that 0 is coprime with any number? Well, basically, the greatest common divisor of 0 and 1 is still 1, because 1 only has one divisor 1. So, in this case, indeed, 0 is coprime with 1, and there are no other remainders modulo 1, so phi of 1 is equal to 1. For n equals 2, 0 is not coprime with 2, because the greatest common divisor of 0 and 2 is 2, and it is bigger than 1. And so 0 is not coprime with 2, but 1 is coprime with 2. So phi of 2 is equal to 1, because there is one number less than 2, which is coprime with 2. For n equals 3, 1 and 2 are coprime with 3, while 0 is not coprime with any number bigger than 1, because greatest common divisor of 0 and integer n is equal to n. If n is more than 1, then 0 and n are not considered coprime. So phi of 3 is equal to 2, because 1 and 2 are coprime and 0 is not coprime with 3. And for n equals 10, it turns out that 1, 3, 7 and 9 are all the integers less than 10 which are coprime with 10. Others are either even or they can be divided by 5, so others are not coprime with 10. And so phi of 10 is equal to 4. Now let's see how to compute Euler's totient function for some particular cases. For example, if p is prime, then I say that phi of p is equal to p minus 1. Why is that? Well, 0 is not coprime with p, because p is more than 1, and their greatest common divisor is p, which is more than 1. And all the other remainders, 1, 2, 3, and so on, up to p minus 1, of course they are coprime with p, because p is prime. So phi of p is equal to p minus 1. This is an easy case. Another case is when our integer n is a product of two different primes. If p and q are primes and they're different, then I state that Euler's function of p times q is equal to p minus 1 times q minus 1. So where to get this formula from? So let us consider all the pq possible remainders modulo pq, 0, 1, 2, and so on up to pq minus 1. We know by the Chinese remainder theorem from the previous lesson that each such remainder corresponds to some pair of remainders rp, rq, rp modulo p, and rq modulo q. So let us arrange all the pq remainders modulo pq in a rectangular table with p rows and q columns, such that remainder r will go into the cell with number rp on the row and with number rq on the column. We know that each remainder r corresponds to a unique pair, so each remainder will go into a separate cell. So now, where are the remainders which are coprime with pq? Those remainders are the remainders which don't have p or q among their divisors, because p and q are the only divisors of pq that can be common divisors with r. So if r is coprime with pq, then its remainder modulo p and modulo q must be non-zero. So in this particular rectangular table, all these remainders are in the rectangle highlighted by orange. These are the cells which have row numbers from 1 to p minus 1, so non-zero row number, and column numbers from 1 to q minus 1, non-zero column numbers, because all the numbers in the 0 row, they can be divided by p, so they're not coprime with pq. All the numbers in the 0 column can be divided by q, so they're not, again, coprime with pq. And all the remainders in this smaller rectangle, p minus 1 times q minus 1, are indeed coprime with pq. And so the number of such remainders, number of such pairs, is p minus 1 times q minus 1. And this is what we wanted to prove. This is the value of Euler's Taussian function for n equal to pq. And in the next video, we're going to prove Euler's theorem that connects Euler's Taussian function with modular exponentiation. Hi! In this video we're going to prove Euler's theorem that connects Euler's Taussian function with modular exponentiation. Euler's theorem is a generalization of Fermat's lethal theorem for non-prime numbers, and together with modular exponentiation it is used to encrypt and decrypt in RSA encryption system. So the theorem states that if integer a is coprime with integer n, then a to the power of phi of n is always equal to 1 modulo n. So this theorem is very similar to Fermat's theorem. For example, if n is prime, if n is equal to p, then we know from the previous video that phi of p is equal to p minus 1. And if we prove this Euler's theorem, then in the case of prime n, we will get that if a is coprime with p, that is p doesn't divide a to the power of p minus 1 is equal to 1 modulo p. And this is indeed Fermat's lethal theorem, which we already proved before. So now let's prove this generalization. Actually, the proof is going to be very similar to the proof of Fermat's lethal theorem. So consider all the phi of n remainders modulo n which are coprime with n. So instead of non-zero remainders modulo p, we are considering the remainders which are coprime with n. Multiplying them by a is invertible, because a is coprime with n, and we know that from the previous module. So the new remainder will also be coprime with n after multiplying by a. So we can again build a graph of remainders which are coprime with n, and we can again get an edge from r to a times r modulo n. And again we will consider this graph and consider what happens if we start with some remainder r and multiply it by a many times. And as in the previous case, if we multiply by a again and again, at some point we'll return back and there will be a cycle. Because in this graph all the incoming degrees are 1, so we have to return to some vertex where we've already been, but it has to be the initial vertex. So again we will get a cycle, as in the proof of Fermat's lethal theorem. And the cycle has length L, it means that a to the power of l is equal to 1 modulo n, because multiplying by a l times doesn't change anything. So a to the l is equal to 1, and all the cycle lengths have to be the same, equal to l. And also these cycles don't intersect, otherwise some incoming degree of some vertex would be more than 1. And these cycles cover all the remainders co-prime with n, because we can start with any such remainder and then generate some cycle. So if there are c cycles, each of them has length l, and they cover all the remainders which are co-prime with n, then c times l must be equal to the number of such remainders, and the number of such remainders is Euler's function phi of n. So in the end, a to the power of phi of n is equal to a to the power of c times l, which we can rewrite as a to the power of l and all this to the power of c. A to the power of l is equal to 1, so this is equal to 1 to the power of c, and that is in turn equal to 1 modulo n. So we proved Euler's theorem. In conclusion, in this last lecture of this module, we defined modular exponentiation. We designed a fast algorithm to compute this modular exponentiation in logarithmic time regarding to the exponent. We proved Fermat's little theorem. We defined Euler's torsion function, and we proved Euler's theorem, which is a generalization of Fermat's little theorem. And in the next module, using all these tools, the Fermat's little theorem, the Euler's function, the Euler's theorem, the Chinese remainder theorem, we're going to use these building blocks to learn how to do public key cryptography, and also we will learn how you can make it wrong and how to break some secret codes if someone used cryptography in a wrong way, and you will break some secret codes yourself. So I'm looking forward to see you in the next module. Hi! In this module we are going to study cryptography. At first, we'll learn how to establish secure communication in case both parties, Alice and Bob, share some secret key. What is the standard way to do that? Then, we will study the most frequently used cryptographic algorithm called RSA, which allows Alice and Bob exchange some information even if they don't share any common secret key initially. And in particular, it allows them to exchange their secret keys using this way of communication. And in the end, we will learn that still there are so many subtle details and so many unexpected attack angles on RSA that, of course, there are some secure implementations, but if you try to implement RSA yourself and miss some of those details, the cipher becomes breakable again. And in the end, you will actually train to break some secret codes yourself. So let's start. Cryptography advanced the most during the last two world wars. That's because everybody was spying on everybody, and still they needed to send some secret communications like attack or don't attack. And the German invented the Enigma machine. This is the photo of a 4-rotor Enigma machine which was invented and used during the World War I. And then the Allies during the World War II, led by Alan Turing, built a computer which broke the Enigma codes. It tried all possible combinations of the rotors and then tried to decipher the ciphertexts intercepted by the counterintelligence, and if what was on the output was looking like English plaintext, that meant that the cipher was decoded. Otherwise it looked like just a random sequence of bits. After the World War, it became clear that to be a superpower, countries need to be able to launch and aim nuclear missiles, and also to defend against them. And the US launched these kinds of radars which try to detect unrecognized flying objects and alarm about the potential threat. And this alarm went through one of the first computer networks to the control center, where the top army officers could make some decisions and react quickly thanks to the quick information flow through the computer networks. Then the universities were first who understood the potential of computer networks, and they appeared in the classrooms. After that, there appeared some startups, and then we got things that we cannot imagine our life today without, like cash machines and money transfers, like email, like online commerce, and like messengers, one of the latest inventions. So what is secure communication? Typically, we describe it as two parties, Alice and Bob, A and B, who want to exchange some information, but they always have to assume that there is always an evil Eve who is stepping on the wire and listening to everything they say to each other. That doesn't depend really on what is the channel of communication. If they are just standing right next to each other, someone could be eavesdropping. If they're talking over the phone, somebody could be listening to the phone line. So anyway, they have to assume that everything they say explicitly is known to Eve. The only thing they can keep in secret is something that they keep to themselves and don't tell to anyone. And so, for example, Alice wants to send Bob some message, like yes or no, or attack, don't attack, something like that. They can invent some cipher, like change word yes to swordfish and change word no to body. But if this cipher, if this algorithm is known, then basically it means that Eve can do the deciphering herself also. And if this cipher needs to be known to both A and B, then probably they have to at some point tell it to each other, so the algorithm will become known. So, in a sense, this type of communication with the algorithm which is public doesn't work as a secure communication. And typically in cryptography we assume that all algorithms are publicly known, because it's too hard to exchange a whole algorithm without it becoming at least partially known to a third party. So the way we can establish some secure communication first in the presence of some secret key is the following. We assume that A wants to send B some message, and message M is a plain text message. It can be encoded as a sequence of bits, M1, M2 and up to Mn, n bits, and that they also have a common secret key K, which has the same length in terms of bits. So it's K1, K2 and up to Kn. Those are all bits. And we assume that somehow both A and B know this key, but they don't have to send it over the network or to communicate it in any way, they just both know it. And then the standard way to encrypt the message is to compute ciphertext C, which is computed as M XOR K, where XOR or exclusive OR is a bitwise operation on the messages of the same length, which does a very simple thing. For any position I in both message and the key, it takes the corresponding bits, MI and KI, and it sums them up modulo 2. It just takes the remainder modulo 2. So CI is also a bit. It is either 0 or 1, because it is a remainder modulo 2. And it turns out that if we add this secret key to message M, not only the message itself changes and if cannot recognize what was in the initial text, if we select this secret key in a special way, it will be not possible for Eve to learn anything about the initial message. Not just decipher the whole message, but she won't be able even to guess one bit of message M with some increased probability. Why is that and how all that works, we will learn in the next video. Hi! What we described as a method of secure communication in the last video is called one-time pad. And in this video we're going to study how to decipher it, why is it actually secure, and why is it called one-time. So what we suggested is to cipher plain text message M if A and B share some secret code K, they need to compute ciphertext as a bitwise XOR operation of M and K. And let's just make some definitions. So A wants to send a message M to B, and we're going to call it with letter M through the whole module. And evil Eve is eavesdropping on every communication and can receive anything that A actually sends to B through the network. A and B don't want E to know anything about M, not just to decipher the whole message, they don't want E to know even one bit of the message M. A and B share a secret key K, and A can send some ciphertext C instead of M. To do that, they use the XOR operation, or the exclusive OR. If X and Y are just bits, they are just either 0 or 1, then X XOR Y is defined as a bitwise sum modulo 2, X plus Y modulo 2. And if A and B are sequences of bits of the same length, A1, A2 up to AN, B1, B2 up to BN, then the XOR of A and B is the sequence of the same length N, such that in each position we do the exclusive OR of the bits in these positions in A and B. And the property that we're going to use of this operation is that A XOR B again is just A. In particular, if you XOR a message with itself, it will be giving you 0, because if you do this with one bit, X plus X, if X was 0, then the result is just 0 plus 0 modulo 2, which is 0. If you take X equal to 1, 1 plus 1 is 2, modulo 2 is again 0. So if you XOR any message with itself, you get 0, and if you XOR A XOR B, you can just cancel both B out, because B XOR B is 0, and then you get A XOR 0, and A XOR 0 is just A for any A, because if you sum anything up with 0 and you take modulo 2, nothing changes. So this is the key to decipher the message. So the communication protocol goes as following. A and B share a random secret key. Random is actually important. A sends B ciphertext C, which is M XOR K. Then B can compute C XOR K, because B also knows the same secret key K. And C XOR K is equal to M XOR K, which is equal to M. So B decodes message M the same way as A encodes M to get C. So now Eve sees only the ciphertext C, which is equal to M XOR K, but she doesn't know K, and she cannot understand anything. And when I say that she cannot understand anything, I mean that basically she cannot guess any bit of the message M better than she was able to before this communication. Why is that? Well, in simple words, if Eve is just given the ciphertext C and the secret key K was random, and I mean it was uniformly random across all the possible combinations of n bits, then the message M, which is equal to C XOR K, all these messengers are equally likely given C, because if you can go through any possible key K as a sequence of n bits, then given this fixed ciphertext C, you can get any message M of n bits with equal probability. So, given just ciphertext C, Eve cannot say anything new about the message M that she didn't know before this communication. What if A and B want to send many messages to each other? For example, Alice wants to send several messages to B. Turns out that they need a separate secret key for each such message. Otherwise, Eve can decipher messages, at least partially. And this is what actually happened in practice. There was a so-called Project Venona by the US, and due to this project, the US deciphered thousands of Soviet Union secret messages that they sent during the World War II in 1941 to 1945. Why that happened? Because, of course, the Soviets knew that they need to cipher their messages, and they used what we've just described, called one-time pad, to cipher those messages, but the process of creating a random key and exchanging it with another party was pretty laborious. And the demand for sending secret messages during the war exploded, and so they just didn't catch up with the load, and so some of the keys were reused. So what was meant as a one-time pad, just one key to encode one message, was actually used as a many-time pad. And then, if you use the same key to encode several messages in plaintext Russian or in plaintext English, it turns out that the eavesdropper can decipher at least part of it. Let's see how that happens. So let's just assume that instead of using the same key once, we used it just 2 times. And so what will Eve see during these 2 communications? First, she will see the ciphertext C1, which is message M1 encoded with the key K. Then she will see the ciphertext C2, which is the message M2 encoded with the same key K. What she can compute then is the XOR of C1 and C2, which is equal to M1 XOR K, XOR K XOR M2. And you notice that I've changed places of M2 and K in this operation, but obviously XOR operation is symmetric, so this doesn't change anything. And in the middle we get K XOR K, which is 0. And you can just remove 0 because nothing changes when you XOR something with 0. So in the end, what Eve will get is the XOR of the initial 2 messages, M1 and M2. And it turns out that if M1 and M2 are, for example, plain English, it is possible to at least partially decipher both, given just M1 XOR M2, because there is some redundancy in the encoding of English language. So, for example, if we know the XOR of M1 and M2 and somehow we know the ith character of M1, character on position I, of course we can already decipher the corresponding ith character of M2, because we know the M prime, which is equal to M1 XOR M2, and this M prime consists of corresponding source of bits on each position, the first position, second position, and up to nth position. And on the ith position, M prime I is the XOR of M1I and M2I. So to compute M2I, we can XOR back the known bit M prime I and the known bit M1I. So if we just know the XOR of 2 messages and some bit in one of them, we immediately know the same bit in another one. How does this help? How do we learn even one bit of one message? Well, it turns out that, for example, plain English messages contain lots of spaces, obviously. So they contain some letters, maybe some punctuation marks, some numbers, and lots of spaces between words. Typically, computers store messages of plain text in the so-called ASCII code. And it turns out that exclusive OR of any English letter with a space in this ASCII code is always different from exclusive OR of any 2 letters. So, if at some position one of the messages contains a letter and another one contains a space, then you will be always able to distinguish this situation from the situation when there are 2 letters on this position. And of course from the situation when there are 2 spaces in this position, because why? Well, because if you XOR 2 spaces you just get 0, and this is different from what you get if you XOR 2 different characters, being spaces or letters or anything. So you can try to find positions of spaces in both messages, and using the XOR of the 2 messages, you will know what are the positions where there is a space in one message and a letter in another one, and then you will just have 2 possibilities of where is this space and what is here in another message. And doing that, you will decode the letters at the corresponding positions. And another thing you can actually use is that plain text English messages are probably going to also contain some very common words, like the word "the" in the English language is the most frequent word, and it is very likely that one of the messages will contain space "the" space in some place, and another message will contain some other words, probably some letters in these positions, and you will be able to guess that, okay, in these 5 subsequent positions we get space, the, and space. And this way you will be able to gradually decode at least some of the positions in both of the messages. Even better if you have not just 2 messages encoded with the same key, but many, like 10. And you'll actually do this yourself as an exercise. So to conclude, the one-time pad using XOR enables secure communication. A and B, to do that, must share some secret key K and use the XOR to encode plaintext message M with secret key K and to get ciphertext C. And they need to use each K key to encode only one message. Otherwise, the one-time pad becomes two-time pad or many-time pad, and it becomes possible to decipher at least part of the message. And if they use the key just once, and this key is really random, then Eve cannot tell anything new about the message being sent, apart from what she already knew about this message before it was sent. But the question is, in the end, how to efficiently establish a common secret key in the first place, because A and B have to communicate somehow to do that, and Eve will be able to eavesdrop on everything they do, we assume. So, in the next lecture, we're going to study an algorithm called RSA, which allows you to do exactly that, even though Eve is listening. Hi! In this video we're going to study the RSA crypto system, which allows Alice and Bob to establish some secure communication even though Eve is always listening and in case Alice and Bob don't share a secret key yet. So RSA is called so because it was invented by Rivest, Shamir and Edelman in 1978. And there is a really interesting story about how several such crypto systems were invented relatively at the same time, but some of them were classified, and this one was public and it was patented, and although it was not supported by the government, gradually it became the most frequently used, and now programs based on RSA are among the most frequently run programs in the world. You can read that interesting story more in Wikipedia, and we're going to describe the system itself. So RSA is an algorithm for asymmetric or public key encryption, as opposed to one-time pad that is symmetric and private key. So this picture illustrates what generally happens in asymmetric encryption. So instead of Alice and Bob sharing a common secret key, just Alice publishes a public key and saves for herself a private key and doesn't tell that to anyone. And if Bob after that wants to send some message to Alice, like "Hello Alice," he can encrypt this message using Alice's public key, which is known to Bob, to Eve, to Alice, to anyone. And then Alice receives this message and she can use her private key to decrypt this message. But no one else knows this private key, and without it, well, it is formally possible to still decrypt, but this is so hard that it cannot be done using the publicly known algorithms in any reasonable time, like in thousands or millions of years. So this is the general schema, and now we're going to describe the protocol. So in this protocol we assume that Bob wants to receive messages. The protocol is asymmetric, so the one who wants to receive messages needs to generate 2 keys, the public key E and the private key D. And if Alice and Bob want to send messages in the direction from Alice to Bob, then Bob generates these 2 random keys. If Bob wants to send some messages to Alice, then Alice would have to generate 2 keys. So in this case we assume that Alice is going to send messages to Bob, and Bob generates 2 random keys, public key big E and private key big D. Then Bob publishes the public key for anyone to access, and then anyone can encrypt message for Bob using E. Not just Alice, but also Eve or anyone else can encrypt and send a message for Bob using this public key. But only Bob can decrypt the encrypted message using the private key D, and this operation is going to be fast and easy to implement. However, anyone can also decrypt by trying all possible keys, because the encryption algorithm itself, the RSA, is public. I know it, you will know it soon, and so anyone can try to decrypt the ciphertext by trying all possible keys, but with the algorithms that are currently published, it would take many years. So this is what we base our algorithm on. We base it actually not on our strong side, but on our weakness, that we don't know how to do something very fast, or at least with some reasonable speed, and this is what allows us to actually send messages securely. So as soon as someone comes up with a very clever algorithm to do the things we currently think are not possible faster, well, every scheme based on this algorithm will become unsecure immediately. So what about the keys themselves? In this particular algorithm, Bob generates first two big random primes, P and Q. And this is where we start to actually use some number theory. So he generates big random primes P and Q, and big means like thousands of bits. Not just some numbers like a few hundreds, but thousands of bits, or hundreds or thousands of decimal digits. That's pretty large numbers. Then he computes their product. This is although it is hard to do by hand, this is considered a pretty easy operation on a computer. So after that, Bob generates also a random number E, which must be coprime with this product P-1, Q-1. You might remember this number P-1 by Q-1 as the Euler's-Tauschent function of n, which is equal to PQ, but we'll talk about that later. For now, this is just this product P-1 times Q-1. So after that, public key big E is just the pair of number n and the small e. And this is going to become known to everyone. And private key big D is the pair of primes P and Q. So people know the product of P and Q, but no one knows P and Q themselves. So we rely basically on the fact that given just their product, you cannot say what were the initial numbers. So the encryption and decryption goes as following. We take message M, which can be encoded as a sequence of bits as usual, and then it is converted to an integer. And to be able to use this message, it needs to be between 0 and n-1, where n is the product of P and Q, which is the public key. So we need to choose P and Q big enough so that this length in bits is sufficient for the messages we want to send. Then, anyone who wants to send message M can create a ciphertext C, which is equal to the modular exponent m to the power of e modulo n. And to do this encryption fast, you use the fast modular exponentiation algorithm from the previous module. To do the decryption, it turns out that Bob can compute and actually pre-compute such number d that c to the power of d modulo n will be equal to the initial message m. So this d is not publicly known, and it's only Bob who can really compute such d fast. But in general, such d exists, and this is what allows us to decrypt quickly, because to compute c to the power of d modulo n, we again can use fast modular exponentiation algorithm. So how do we compute such d and where to take it? So let's assume we already have this d. What needs to happen then? So c is our ciphertext. We make the exponent c to the power of d. This is equivalent to taking the initial c, which is equal to m to the power of e modulo n, and then taking the d exponent of that. So m to the e and all that to the d. And this is equal to m to the ed modulo n. So what we need is that m to the power of ed modulo m is equal to message m itself. Now, we know that n, the modulo, is equal to the product of two primes, p and q. And of course, those are two different primes, so they're coprime, so we can use the Chinese remainder theorem here. And by Chinese remainder theorem, this modulo equality m to the power of ed is equal to m modulo n is equivalent to two new equalities. M to the power of ed is equal to m modulo p, and m is equal to m to the power of ed equal to m modulo q. Because p and q are co-prime, we use the Chinese remainder theorem. Now, how to achieve that? We need these two equalities. They're pretty similar, just modulo different prime numbers. As these are prime numbers, we can use the Fermat's-Little theorem. And we know that with Fermat's-Little theorem, we can optimize the computation of modular exponent, and in particular, for any m and any k, m to the power of k is equal to m to the power of k modulo p minus 1 modulo p. So, the above will hold if ed is equal to 1 modulo p minus 1 and ed is equal to 1 modulo q minus 1. Because we just, instead of taking m to some exponent equal to m to the power of 1, we just take the exponent ed and say that it is going to be equal to the exponent 1 on the right hand side of the above equation, modulo p minus 1. And the same modulo q minus 1. So this is what we need again. This is not what is already satisfied, this is what we need. And again, to satisfy this, we can make an even stronger request. We can request that ed is equal to 1 modulo the product of p minus 1 and q minus 1. If this is true, then of course the above is also true, because p minus 1 and q minus 1 are divisors of p minus 1 and q minus 1, and we know that the remainder modulo a number defines the remainder modulo any its divisor. So, remember that when Bob generated E, we required that it should be co-prime with p minus 1 times q minus 1. This is what is going to help us now. So Bob can use the extended Euclid's algorithm to compute such d that ed is equal to 1 modulo p minus 1 q minus 1. Why is that? Because e is co-prime with the modulo, so multiplication by e is invertible, and so there is an inverse element d which gives 1 after multiplying by it modulo p minus 1 times q minus 1. So not only it exists, but we know the algorithm to do that, and this is called extended Euclid's algorithm. So the decryption algorithm is compute p minus 1 times q minus 1. Bob knows both p and q, so this is easy to do. Then compute d, which gives ed is equal to 1 modulo p minus 1 times q minus 1 using the extended Euclid's algorithm. And actually Bob can compute and store this d right after generating numbers p, q and e, and then use it and not just compute it every time someone sends a message to him. So to decrypt the ciphertext C, he will just compute the modular exponent of c to the power of d modulo n using fast modular exponentiation algorithm. And the communication protocol is as following. Alice represents message m as a number between 0 and n-1. She computes and sends the ciphertext m to the power of e modulo n. Bob receives this c and computes m back by c to the power of d modulo n. So, what do we use here? We know that n is publicly known, but its factorization, prime factorization, is secret, and we rely on the difficulty of factorization. If someday an efficient integer factorization algorithm appears, RSA will immediately become insecure. But as for now, we don't know any efficient algorithm for factoring big integers. Actually, we also rely on the fact that it is difficult to compute the number p minus 1 times q minus 1 without knowing p and q. Otherwise, even if Eve couldn't factorize n, she could still compute d, because it only uses this p minus 1 times q minus 1 number. However, computing this number, which is actually Euler's-Stauchen function of n, is equivalent to factorizing n. We can show that if you can compute this number, then you also have an efficient algorithm for factorizing n in the first place. And encryption and decryption can be equivalently explained using Euler's phi function and Euler's theorem instead of Fermat's-Little theorem to note that for any m and k, m to the power of k is equal to m to the power of k modulo phi of n modulo n. And you can do this as an exercise following the slides where we explain the same using Fermat's-Little theorem. In general, to decrypt, we don't even need the p minus 1 times q minus 1. All we actually need is to solve the modular root problem. So you are given the ciphertext C and you are given the public exponent E, and you need to find such M that M to the power of E is equal to C modulo N. Or, which is the same as find the modular root of C, but not just regular root of a number, but just eth modular root of C. Again, there are no known efficient algorithms to solve this problem. However, there are known algorithms which solve modular root problem and avoid factorization. So in theory, it could be possible to solve this problem efficiently, but still not solve the factorization problem efficiently. So these two problems are not necessarily equivalent. However, all the known algorithms that do that are still inefficient and the scheme is still secure. So the cryptanalysts have been working on different attacks against RSA for decades, because it is always a science of coming up with a cipher and then trying to break it from different points of view. There are, of course, accurate implementations which aren't broken, or at least aren't very much broken. Still, regularly we see some attacks which break some ciphers. However, there are a lot of subtle details, and missing them leads to a breakable cipher. And you will learn in the next lecture several attacks and break several ciphers as an exercise. So, see you in the next video. Hi! In this lesson we are going to study the attacks against RSA. Although RSA is a secure crypto system, there are a lot of subtle details in the implementation, and if used incorrectly, it is actually possible to break the cipher. And you should listen carefully, because you're going to actually decipher some ciphertext yourself as an exercise. I think these are pretty cool problems, but to solve them you need to really understand what's going on in the lecture. We'll start with some simple attacks. First case is Alice wants to secretly transmit a message to Bob. So Alice and Bob are secret agents, or Alice is a secret agent and Bob is sitting in the center. And Alice needs to either transmit that the center should attack or don't attack to Bob. So she can convert the message attack to message m equals to 1, and don't attack to message m equals to 0, and then use RSA to encrypt m with some public key and send the ciphertext C so that the center can decrypt it using its private key. So all in all, we're using only the secure algorithms. Everything should be okay, right? Well, actually it's not, because unfortunately it's really easy to break this particular cipher. Just try to encrypt both m is equal to 0 and m is equal to 1 with RSA the same way, and then check which one of them results in the ciphertext C. And the one which coincides with the ciphertext that Alice is going to send to Bob, this is what was initially encoded. So the algorithm RSA is publicly known, the public exponent is publicly known, so anyone can take both messages 0 and 1 and encrypt them to get the ciphertext, and then compare this ciphertext to the one that was actually sent. And this works with any small set of possible messages. If you have not 2 messages but let's say 100, still an attacker can just try to encrypt all of them, see which of the ciphertext coincides with the ciphertext that you send, and then he can decrypt your message. So this is really a practical situation. Of course, not often you need to send just one of 2 messages, but it is very often that you want to send one of a very limited set of messages, and it is predefined. So what to do to solve this problem? The solution is to use randomness. So for example, you can always use the first 128 bits for the message itself, and then you also append some 128 more just random bits before encryption. So for Bob it will look like he will be able to read the first 128 bits in plain English or other language, and then the other 128 bits he won't just use, he won't look at them, they are meaningless. But this simple attack already won't work, because to try all possible messages, the would have to not only try the first 128 bits filled with one of the predefined messages, but they would actually have to go through all possible combinations of the second half with 128 bits, and that's already 2 to the power of 128 possible messages, which is basically impossible to try all of them out. So at least this simple attack won't work if you use some randomness before sending the ciphertext. Another way to attack the RSA is, for example, Bob generates two random primes P and Q, and then he publishes the public key. But what if one of those primes P turns out to be less than 1 million? Then Eve, which is eavesdropping, can try all primes up to 1 million as the potential divisors of the publicly published key n, and she will get the factorization of n, P times Q. And then she will be able to do the same thing that Bob does to decrypt any message that is being sent. So if one of the primes is small, we can actually solve the factorization problem, and that is why we can decipher the ciphertext. So one typical solution to this is to generate random primes for the secret key uniformly among very large numbers. For example, you only generate primes which have 2048 bits. Then these primes will be guaranteed to be big enough so that no one can go through all possible values of these primes. So these were two pretty simple attacks, and we're going to discuss some more advanced attacks in the next videos. Hi! In this video we're going to study a bit more subtle attack, which uses a small difference between primes in the public key. So assume that Bob generates primes P and Q such that P is less than Q, and the difference Q minus P is somewhat small, like 1 million. What can Eve do in this situation? What do you think? Well, we see that n is equal to P times Q, and P is less than Q, so P should be less than square root of n, and Q should be bigger than square root of n for that to be true. And Eve doesn't know P or Q, but she knows that this property is necessarily true, that one of the primes is less than the square root of n, and another one is bigger than the square root of n. Now, we can also say that square root of n minus p is less than q minus p, because square root of n is less than the bigger of the two primes. Q minus p is equal to r, which is small, and so now we can say that square root of n minus r is less than p. Okay? And then also we know that p, the smaller of two primes, is less than square root of n. So now we have a range between square root of n minus r and square root of n, where necessarily one of our prime divisors of n lies. So p is lying in this range, and the length of this range, what's it? Well, it's just r, which we said to be pretty small, like 1 million or something. So what we can do is, we can actually, if we're playing for Eve, we can try all integers in this range between square root of n minus r and square root of n as divisors of n, and necessarily we'll be able to factorize n. And to try just 1 million divisors is, we can do that pretty fast. So this leads to us breaking the cipher. Actually, we can do this even more efficiently, because if n is a product of two primes, well, of course, P and Q will be both odd, because it doesn't make any sense to use prime number 2 as one of those, because it's small, and we already know the attack on the RSA when one of the primes is small. So then both P and Q are more than 2, and so they're both odd. So numbers P plus Q over 2 and P minus Q over 2 are integers. Now n is equal to P times Q, and we can rewrite that as P is equal to P plus Q over 2 plus P minus Q over 2, and Q is equal to P plus Q over 2 minus P minus Q over 2. So we can rewrite n as a product of these two brackets, and then this product is equal to difference of squares of P p plus q over 2 squared minus p minus q over 2 squared. So n is a difference of squares, and one of the squares is small because the absolute value of p minus q is given to be small. So what we can do to decipher or to factorize n, at least we can try adding the increasing squares of integers to n, like try n plus 1, try n plus 4, try n plus 9 and so on, n plus some small number squared, until the number that we get becomes a perfect square. So if we get n plus some square is equal to some other square, then we get that n is a difference of squares. So of course we can use the formula a plus b times a minus b to factorize the difference of squares. So, and this is guaranteed to work because we know that some square of a number less than, let's say, 1 million is going to work. So we will just try all these numbers and try to factorize n. So this can be done probably even faster than the previous version of just going through all possible p in the range. So the solution to avoid this attack is to not just generate p and q, but if we generated p and q and it turns out that absolute value of p minus q is small, then we can just regenerate and repeat until the absolute value of p minus q is sufficiently large. But actually, in practice, if we're using a good random number generator and we're generating really big primes, like primes of size 2048 bits, then the probability that this happens is negligibly small. So we can actually even ignore this problem whatsoever and just generate primes uniformly among all big integer numbers of 2048 bits, and the probability that we'll get this problem is so small that we don't need to bother about it. The probability that someone will just go and tell our enemy our secret key is much bigger than the probability that this algorithm will actually generate two primes which are too close to each other. So although this is an interesting attack, this is more of a theoretical attack which shouldn't happen in practice, and we don't have to actually defend ourselves against it. The only way we need to defend us is to really use uniform distribution on the numbers when we generate big random primes. Hi! In this video we're going to study an interesting attack which takes advantage of many different devices using encryption and the fact that sometimes there is insufficient randomness, so to say, to generate the keys when they're generated. So this attack was invented by Henninger et al. And Lenster et al. And this is actually a practical attack. So they used public keys from a set of different devices and they used them to decipher some of the private keys, and the experiment resulted in 0.4% HTTPS keys were factored, which is not a big percentage, but this is actually a pretty big number. So a lot of communication that was considered to be secure turned out to be decipherable using public keys from different devices which use the same algorithm to encrypt. So this is a code which is not the exact code, but some code that resembles the OpenSSL popular program RSA key generation. So first we initialize the random number generator RNG as an instance of class random number generator, and then we seed it rng.seed with some random seed. And we need to get this seed from somewhere. If we just hard-code some fixed number like 1, 2, 3, 4, 5 as a seed, then it won't be actually a random number generator. It will always generate the same sequence of numbers because it's not a real random number generator, it's a pseudo-random generator, and they work as following. They get some initial seed and then they generate some sequence of numbers which looks like random, but it is determined by the initial seed completely. So typically what programs like this do, if they work on someone's computer, they ask the user to maybe move a mouse for some time to get some randomness from the timings of the mouse, or if this is for example on a router, then it can take the current time as a seed or some of the contents of the network packages that it has listened to. So we seeded our random number generator, after which we generate the first random prime number p as rng.generate big random prime, please. Then we further improve our random number generator maybe by adding some randomness, like take some bits from memory and seed our random number generator even more with these bits which hopefully collected some more information from outside, which could be treated as random bits. So then we generate another big random prime number q, and then we compute n, which is equal to p times q, and publish this n as a public key. So what can be a problem here? The problem is, what if the seed is not random enough? Well, it is hard to measure randomness, so these are truly just words, but the example of what I'm referring to is that keys can be, for example, generated by the network router immediately after startup. So no incoming network packages were accumulated yet, so we cannot use any external information sent to the router as a source of randomness. And on some of the routers they don't use any hardware randomness generators, which use some random physical processes to get some real randomness from. So in this case nothing is left as to use something like time as the seed, and there are not so many variants of value for time, so it can happen that sometimes, not very often, but sometimes the same prime number p will be generated as the first number just right after seeding, because sometimes the seeds will coincide on different devices. So then the random p is the same on two different devices. After that, our random number generator is again seeded with something, maybe with time again, or maybe already some network packages came into the router, so something changed, and now we generate another random number q. And although it can happen that q will also coincide, but this is not very likely. I mean, if the first number is only 0.1% likely to coincide, then the second number is also at most 0.1% likely to coincide. So if the first number already coincided, with 99.9% probability, the second number will not coincide across these devices. So what we will get in the end is that one public key will be generated as p times q1, and another public key on another router will be generated as p, the same p times q2, which is different. So what can we get from there? If the public keys n1 and n2 are generated on different devices using the same p but different q, then the greatest common divisor of those two public keys n1 and n2 is equal to p, because p is prime and it is a common divisor, but q1 and q2 are different, so the only common divisor is just p. And using the simple Euclid's algorithm, we can compute the greatest common divisor of n1 and n2, which is going to be p. After that, we can just divide n1 and n2 by p and factorize both n1 and n2. After that, our public keys break into private keys and our encryption scheme is broken. So we can take keys from many routers and try to combine all pairs. We don't know which routers generated n1 and n2 with the same prime, but if we just try to take all pairs and try to compute quickly their greatest common divisors, at some point some of the pairs will give us the coinciding p, and we will be able to decipher these public keys. And this is what actually the scientists who came up with this attack did with public traffic and public keys, and they were able to decipher 0.4% of all HTTPS keys. So to avoid this attack, this is much more subtle, as you probably noticed. You need to make sure that the random number generator is properly seeded before you start generating your prime numbers. And there are many ways to do that. On the routers you can use some hardware physical randomness generator, or you can avoid generating keys right after startup. You can first listen to some incoming network traffic to get some random bits from the incoming messages and so on. And if you're, for example, writing a software for a personal computer, then some of such computer programs that need to generate keys ask the user first to move the mouse for some time to get randomness, and then they rely on the actual person to do some random movements with the mouse with some random timings and random positions, and then they get the random number generated seeded using that kind of randomness. Hi, this is our last video on the cryptography module, and we're going to study the Heystad's broadcast attack. It's a very interesting different type of attack. So first we studied some simple attacks based on wrong implementation of RSA, or on some prime numbers being small or difference between them being small, and on some insufficient randomness, which turned out to be a problem. This is an attack from a completely different angle, which comes from the fact that sometimes we want to send the same message to many different recipients, to broadcast this message. And if we do that not careful enough, then it can be a problem. Someone can break our cipher. So Heystad came up with an attack in case Bob sends the same message to several recipients using their public keys. And it uses the fact that it's basically the same message, and it doesn't change at all. It doesn't use any randomness, and that is key for the attack. It works in a very general case, but we will consider a very simplified case as an example of how we can break this code if the same message is broadcasted. So let's imagine that Bob wants to send the same message to Alice, Angelina and Adriana. So he has the message M, and he wants to send this message to all three. But of course he doesn't want for anyone to listen, and he wants to send this message as a secret, so instead he will use the RSA algorithm to compute three ciphertexts. Ciphertext C1 will be m to the power of E1 modulo N1, where N1 and E1 is the public key that Alice provides to send messages to her. C2 is equal to m to the power of E2 modulo N2, and it is different. It is using a different public key, N2, E2, and the same with the third message, m to the power of E3 modulo N3. So in our simplified case, we assume that all E1, E2 and E3 turn out to be equal to 3. This potentially could happen, and what happens in this case is that C1 is equal to m cubed modulo N1, C2 is equal to m cubed modulo N2, and C3 is equal to m cubed modulo N3. So what happens next is that the greatest common divisor of any two different public keys is equal to 1. Well, otherwise, we just learned in the previous video, if some two public keys are not co-prime, then we can factor each of them and anyway decrypt the messages. So we assume that we somehow avoided this problem. These public keys don't have any common divisors, they are co-prime. As they are pairwise co-prime, we can use the Chinese remainder theorem, and in particular we're going to use it to construct such C that, of course, this C is a remainder modulo the product of these three modules between 0 and N1 and 2 and 3, and also C has the same remainder modulo N1 as C1, the same remainder modulo N2 as C2, and the same remainder modulo N3 as C3. This is not just possible, this is possible and can be done using an algorithm we learned in the previous module, which is based on the extended Euclid's algorithm. So you first construct the number with the required remainders modulo N1 and N2, and you get some remainder modulo N1 times N2, and then using the fact that N1 and 2 is co-prime with N3, you construct another number which has the required remainder modulo N1 times N2 and the required remainder C3 modulo N3. And then in the end you get a remainder modulo N1 and 2 and N3, which has required remainders modulo N1, N2 and N3. So If we use our algorithm to construct such C, then it turns out that C will be equal to m cubed modulo n1, n2, n3. Why is that? Well, again, by Chinese remainder theorem, because C gives the same remainders modulo n1, n2, and n3 as m cubed from the above equations. And this means, as n1, n2, and n3 are pairwise coprime, that C and m cubed have the same remainder modulo the product of these modules. Now we know that C is equal to m cubed modulo n1, n2, and 3, and also we know that C is between 0 and n1, n2, and 3, because C is just a remainder modulo this product, and also m cubed is also between 0 and n1, n2, and 3. Why is that? Well, obviously it's non-negative, but also m is a message sent using public keys n1, n2, and n3, so m must be less than n1, n2, and n3 just to be used in the RSA scheme. And as m is less than each of these modules, by multiplying these inequalities we get that m cubed is less than their product. So these two numbers have the same remainders modulo product n1, n2, and n3, and they are between 0 and n1, n2, and 3, so they are both remainders modulo this product. And it means that these numbers are just equal, because there are no two different remainders which are equal. So C is equal to m cubed in the end. And then, if we know C, we constructed it using Chinese remainder theorem and Euclid's algorithm, then we can just decode m by computing the regular cube root, not just some fancy modular cube root, but just the regular cube root of an integer number C to get m. And this is the way hasted attack works in this simplified case. So we just need to apply extended Euclid's algorithm to construct number C, and then we just compute the regular cube root. We can do that in floating point arithmetics, but then just round up to the closest integer, and it will turn out to be the exact message that someone sent and if intercepted the ciphertext. So broadcasting the same fixed message is a problem, and Heidstadt's original attack works not just with the case when all E1, E2 and E3 are equal to 3 and when there are 3 recipients. It works even with bigger and different EI and with a different number of recipients if there is enough recipients to apply this attack. So the solution to avoid this attack completely is to add random padding to m before encryption. Why that works? Because then it is impossible to compute m using all the ciphertext just in some deterministic way, because each CI includes some random part apart from m, and so there cannot be any deterministic algorithm that recovers the exact m out of C1, C2 and C3. So C1, C2 and C3 share some common information in the form of m, but they also differ by some random bits which we added to m before encryption, and so we cannot actually use such kind of algorithms to recover m. So general idea is it's a good thing to always apply some randomness, to always leave some amount of randomness in your message before encrypting it, because it allows to avoid many different attacks, from the easy one with the limited initial message set which we studied in the beginning, to this advanced Heistadt's attack, which also is not applicable if you add enough randomness to the messages before encrypting them. Apart from algorithmic attacks, there are some attacks that use the physical world around us and the properties of the algorithms and the hardware that we use to actually implement those algorithms. For example, the time to compute c to the power of d modulo n can at least partially expose d, which is not a part of a public key, and if someone knows d, then he can decipher any message, and it's maybe hard to imagine this situation, but actually if there is a web server with which you can communicate and you can send ciphertext to this server, which it then decrypts and based on the contents of the decrypted message responds something back. If you communicate with such a server and then measure the time of response, then you can actually try to send several times the same ciphertext, measure the time to compute c to the power of d very accurately, and then make some conclusions about d that was used to get the ciphertext that you intercepted. So this is one example of a problem. Another example is that sometimes web server is configured to respond with an error return code if you send an incorrect ciphertext. And if you, for example, intercepted some ciphertext that was generated using RSA, then there are some ways that you can change this ciphertext to be looking still like something encoded with RSA, but which results with an incorrect message if you decipher it. For example, if you know that the message was encoded as m to the power of e modulo n, you can, for example, multiply it by 2 to the power of e modulo n, and it will look as if you encoded message 2m instead of message m. And then the server will decipher this, and if the message 2m doesn't make sense to him, it will send you an error code, and then you will understand at least something about this new message 2m. And by doing this many times, you can recover enough information to decipher the initial message. And the last, maybe even more surprising attack is that not only time or error codes, but power consumption of some part of the hardware you're using, the power consumption while computing c to the power of d modulo n can expose some information about d. It's even harder to understand what's the problem here, because if you already can come to Alice, to her home, and then get access to her computer, then probably you can just read her information right on that computer. Why do you need to decipher anything? But actually there are some situations like this when you have access to the hardware, like if someone has stolen a computer and this computer had an encrypted hard drive. So someone cannot just read any information from that hard drive without decrypting it, but then this someone can measure the power consumption while computing the decryption by the algorithm itself, and then it can decipher at least some information about D, and then use brute force algorithms to recover the whole D. Another situation is when you're just interacting with a cash machine or ATM, and you use a stolen card, and then you try to get some money from it. The ATM internally tries to decipher something every time you're trying to input a PIN code, and if you have access to the ATM machine, you can measure the power consumption of it during the decryption process, and then again you might be able to decipher the message completely or partially, and then try much less PIN codes to actually withdraw some cash. So in conclusion, RSA is of course a very powerful method which is used everywhere, literally everywhere. This is literally the most frequently run software in IT, but it is hard to implement correctly, and correctly is very hard to say what is correct, because the attacks always appear from unexpected angles. The system and the algorithm itself is relatively simple, but there are so many ways that we can break, either using information from different devices that use the same algorithm, or using information from the same message sent to many recipients, or even measuring time or error codes or power consumption of devices that are implementing these algorithms. And you have to account for all that in your implementation so that no one is able to exploit those attacks. So if you want a deeper dive in RSA and encryption and decryption algorithms, you should take some dedicated cryptography courses which are available at Coursera. And now we finish with our lectures in this course, and I wish you to have fun with the problems that we've prepared for you, because you're going to actually break some ciphers. And I think that will be pretty cool.